Welcome to APEC. It is August 2nd, 2025, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everyone watching us on YouTube. We have a ton of stuff going on right now. In theory, Al Baur will be showcasing experimental advances in electrostatic levitation today. John Brandenburg will be discussing the physics of time and talking about 3I Atlas. Matthew Szydagis will be providing an overview of his upcoming course, The Physics of Exotic Propulsion for Interstellar Space Travel. And Charles Buhler, in a pre-recorded video, will be discussing Exodus and the Third Order. We're also going to have updates from our lab partners and finish off the event with an open discussion by conference attendees. So today's event is on StreamYard, broadcasting through the Alt Propulsion YouTube channel. Please subscribe if you haven't done so already. Also, you can ask questions using the live chat feature on the right-hand side of the screen. We will try and get them over to our presenters, depending on time constraints and how fast they scroll up and off the page. You can also always view conference replays, details, and speaker info on our website at altpropulsion.com. So, a couple of quick updates. Next weekend, I will be visiting Isaiah Ritchie's lab in Portland to capture more footage of his SEG work, including new roller magnetization process. I know that I said this last conference. I had some snags in the schedule, so that is back on the list, and I am super excited. He's got a bunch of stuff going on. He has constructed new stuff. He is pushing forward. Again, Isaiah is probably the #1 SEG builder in the world right now, at least. The work he's doing is absolutely incredible. I recorded a 1-hour presentation with Dr. Charles Buhler, who is the colleague of our good friend, Andrew Arigna. And Charles basically rolled through his new model of physics to try and explain some of the results that Drew presents on all the time. So I'm going to basically play that today, and I have a longer version of that with some Q&A up on my channel as well. I'll drop a link in. So I think those are kind of the big things, and we just have lots of stuff that's kind of coming and going, and we'll get into that as we go. Okay, so we're going to do things a little bit different today. As you can see, I may look a little different. We're having some tech issues. I'm going to bring in the usual suspects as well. So our first presenter, Al Baur, is not here, guys. So, yeah, this is APEC the way it was meant to be. Real, raw, disorganized. So what should we start with? Should I start with the Buhler video?
I've got some. I can show some slides before or after the Charlie. So your call, Tim.
Okay. Well, yeah. Let me go in here.
I can't believe you got a precious block of Dr. Buhler's time. I can't even get his time.
Okay, so let me try and do. Oops. Okay, what I'm gonna do is share this tab. Let me see if I can do this correctly. Yeah, and you know what? I should not pick on. I will not pick on Al Baur. Al is in Israel, and so they are way ahead of us in terms of time. So. Okay, so there's that. So I think if I maximize this, it'll play. But let me start.
All right, so this is title of this talk is Exodus and the Third Order.
There we go.
I'm going to tell you what that means here in a moment. But first, I want to talk about what we've been doing that's not Exodus related. We have been quite busy, Tim. As you mentioned, we have been removing dust on the moon. This is something we've been doing for 25 years at NASA. So we just got our EDSs, our electrodynamic dust shields, operating on the lunar surface in March of this year on the Firefly lander, part of the Blue Ghost mission. So you can see that we can clean glass and thermal radiator surfaces free from dust on the lunar surface, which is very exciting. In addition to that, we're sending humans back to the moon and Mars, so that's been keeping me very, very busy. But the Exodus team is working on other technologies, not just propellantless propulsion.
Okay.
So Exodus has been busy. We've continued the development and experimentation on new class of thrusters. Drew will talk more about that. Ongoing experimental validation of the Exodus force by others. So this is a big one, Tim. Since the last we've talked, we were able to perform the Exodus effect in other vacuum chambers, so it's not a test setup issue. They were verified at other laboratories by other groups, which is absolutely necessary. There were even Exodus test articles that were built, developed, and tested at other locations. So this is how we get this theory into practice in the real world, is to have other researchers design these, test them, build them in their own chambers, their own facilities, and that has been started, which is outstanding. So there's this is really good news for us, for Exodus. We knew it would. We knew it would work. So we're not infinitely surprised by that, but it is exciting to see this actually happen in the last year or so. So that's been fantastic. So but we always get the question, where does the force come from, right? The classical electrostatic pressure force and the divergence force, which we call the divine force, the divergence in electric field, doesn't adequately explain the generation of the forces. They are derived from the conservation of energy in the classical limit, but it doesn't really show you where the forces come from. So today we're going to try to tackle that. Okay, and so what do we know? We do know that we're dealing with a quantum mechanical effect. We know that from the experimental necessity of the fine structure constant, which is a purely quantum mechanical variable. We know we're in the low energy limits of quantum mechanics. We're not splitting atoms. We're not generating very high energies. We're not doing anything in the high energy limit. These are test articles and voltages that people have common access to. We truly believe that this phenomena can and should be explained within known physics. We don't think there's a need to invent something new, and I think that's a very important point. So usually what happens is, people come up to me or they send me things about research that they've done, and then 9 times out of 10, it's something that's completely new, completely revolutionary, completely, crazy, out of this world stuff. And I love getting that. I'm not going to lie, I do love getting that. But really just don't have the bandwidth to start from there. So what I've been hoping for is to have some physicist kind of try to help me explain this with known physics, because I think we have the tools already to do that. I don't think it's necessary to reinvent all of physics, especially for the last 200 years, and start from scratch. I don't think that's necessary. So as we move forward, we want to keep in mind that we're trying to stay within the bounds of known physics, and that's important because there have been many outstanding researchers that have worked on this for several decades, even centuries. What else? Where do we start? So we know the force is fundamental, and that's important. It should be able to act on individual particles and not just large particles or large systems of particles. The electrostatic pressure force on a single particle, regardless of their sign of proximity from another. So we should be able to see this on just single particles. We don't need giant structures to see this. This should affect every particle. We do know that Coulomb's law should dominate, but it's entirely possible that a much weaker, higher order term plays a role in the observed forces that we see. So when we start thinking about weaker, higher order terms, that lends us right to perturbation theory, which has been used to describe the Coulomb law of interaction between two particles to the second order. So this is where we're going to begin. So to do this, we need quantum electrodynamics. So we have to talk about QED, and I apologize to the whole audience for talking about QED. It's not something that people want to hear about, but it's probably a necessary evil that we have to go there. And we'll explain why we do that. Perturbation theory, this is kind of how it works. So essentially, some of the perturbation theories are are on the orders of alpha. So alpha is the fine structure constant. It's this weird number in nature. It's 1 over 137 that keeps popping up. Do not ask me where it comes from. I'm not going to tell people I know where it comes from. But since we've seen that in our experiments, we think that we are dealing with a perturbation theory. Basically, you start with an unperturbed system of energy, you make a little change to it, quantum mechanics, and then you see what the new energy is, you find out the new states, and then you start again with the second order and going to the third, going to the fourth. This has been done for the Bohr energies of the hydrogen atom. You can see different orders of energy based on whether it's the actual Bohr energy itself, fine structure constant, Lamb shift, hyperfine, splitting it, and etc. So there are many examples of this in quantum mechanics, and perturbation theory really is probably the greatest discovery in all of quantum mechanics. Is all of the great discoveries have been done caused by perturbation theory, which is pretty exciting. So, but before we get to that, we're going to show you where we're starting from, and I think this is important because there are other forces that come from where we're beginning, our background. What is the background? And the background that we're all in, where we're starting, is the background of the infinite quantum vacuum fluctuations. So the vacuum fluctuations, what the heck are those? So essentially, we live in the sea of this infinite energy that are called quantum vacuum fluctuations. And energies are just defined by this h bar constant times omega. You don't have to know all of this stuff, but I'm keeping it here anyway for the users, Tim, so that when people can read this, they can go through later and they can fill in all the parts. What I really want to come across is the concepts. The math doesn't matter. The concepts are what's important. So for something as simple, not simple, but something, for example, as well known as the Casimir effect, how does that work? Well, what you're really doing is you have these fluctuations in 3 dimensions, and you constrict it in one of those 3 dimensions. So these Ks are basically wave numbers. They basically have units of 1 over length. And what that is how we characterize energies. We do it in 1 over length. The same way we use frequency to use sound, we use frequency to use sound. We don't use time domain to talk about sound. We use frequency, which is 1 over time. The same thing with K, it's 1 over space. So we have space and time. We have 1 over 1 over length is our K number. Makes things very, very easy for physicists. We don't have to deal with inverse space. We can just use K right away. But so all we do here is we just do in Casimir effect, we just essentially take this integral, we turn this energy into an integral, and we just integrate it over all space. We can do that in the X and the Y, which are continuous, but if we have flat plates in the Z direction, we constrict them. And we know how to do that from quantum mechanics. We put in a series expansion. And when we do that, we have a difference in energy of the one that's not constricted minus the energy of the one that is constricted. So the process here is to find what is that change of energy. When you do that, take its derivative, and you got the force. Boom. So your process is actually that simple. Find out what is your background energy, make a little tweak to it, subtract them, then you got your force. That's how Casimir did it. Now, Casimir is subtracting states away from the vacuum. So he's constricting the actual number of states in the vacuum. We're not going to do that. We're going to add states. So I'll show you what we're going to do. So, perturbation theory. How do we use it for our case? Well, I'm going to start from the very simplest case that we can think of. And that is the case where we have 2 electrostatic charges, Q1 and Q2, at some distance R1 and R2 away from the source. Now, to do this, we have to do, when we start adding charges, we add them into the background of, this is the hard thing to say. The hard thing to say is it's in the background of these quantum vacuum fluctuations, these states. So we're starting from 0. But the states are not actually at 0 energy. There is some energy above that. So we have, instead of using a Hamiltonian and getting equations of motion, is what you do in classical mechanics, you start with a Hamiltonian and you operate on states to get an energy out of it. And that's what we're looking for. We're looking for the lowest energy state. And the first energy state I'll show in a minute has no consequence. It doesn't change anything. But if I take these two charges and I put them in the vacuum, how does that energy state change? Just by doing that simple thing. I'm bringing two particles, I bring them in. How does that change the energy state of the universe? And add it all up, see what you get. Well, people have done this. So what I'm going to go through is I'm going to go through this horrible math, but I'm not going to go through it in detail to show you how you can use second order perturbation theory to come up with Coulomb's law, reals, which is what everyone knows. So we have these basically two terms. Our change in energy is going to be this first order term. Now these quantum mechanics are a little weird. You have to read it from right to left. But you start from a zero state, you add your coupling term, and then you finish with your zero state. You figure out what that change of energy is. Oops. And then you have a second order term. You do it again, but this time you insert some additional states. And I'll show you what that is in a second. So what we have to do is we have to define a coupling. H0 is the free charges in the system, or the free fields in the system. In this case, it would be the free fields. That is basically the ground state of the universe. Now we add two charges, and how do those two charges interact with that? Well, they act through this coupling, this AJ. A is the vector 4 potential. This is a very strange thing. You don't have to memorize this. This has all the information of the quantized electric and magnetic fields in it. That's all you need to know. It is actually the quantum version of E fields and B fields. It's all there. Someone else did this math a long time ago. I'm not going to go through that. This is the 4 current density. Whenever we say 4 currents, we're talking space-time. You have one time dimension and 3 space dimensions, and that's how all quantum mechanics is written. So we have our 2 charges, and they're located at R1 and R2, and the other 3 dimensions are 0. So we have 2 static charges sitting there in time, not doing anything. So we just multiply these two together. We get this awful equation. And I kept the second order perturbation theory equation up here. And now we have to find out what all these little terms are. So you expand it out a little bit. And this is a really kind of a good graphic here. You start from 0, you go through the coupling, you get to a new state K. What does that mean? What it basically means, you have nothing. The coupling creates a virtual photon out of the vacuum, and it ends up in state K. If that new photon state K interacts on that coupling again, comes back down to 0, then that's a non-zero result. This is all I can tell you. So essentially, you have a 0 state, you act on what is called the creation operator, and you get a state K. On this other one, you have a state K, and you act on the annihilation operator. You go back to state 0. So you start from 0, go up to K, K to 0. Boom. Those are the only non-zero matrix elements for this simple case. In second order, because these are very strange things called, they are called photons. They're actually called virtual photons or scalar photons. They have this selection rule where that product is -1. We'll talk more about that a little bit later. But you do all of that math, you come up with, you solve these equation, and you multiply these out, you get these 4 terms. You get a Q1 squared over 4 pi epsilon naught R1, Q2 squared over 4 pi epsilon naught R2, and then Q1, Q2 over 4 pi epsilon naught R1 minus R2. This first one is the self-energy of the electron. The second one is the self-energy of electron at position 2. And the third one is the Coulomb interaction, Coulomb energy between both of them. So you actually get Coulomb's law starting from this covariant form of quantum electrodynamics. It's a very difficult way to do it. There's no doubt about it. But it actually does give you the right answer. So this is what you're trying to find. This is the force or energy of interaction between 2 charges, if they repel or they attract. And it all stems from solving these equations, which are not the simplest in the world to solve, because you have e to the I kr over k squared. They're very, just takes some calculus there to do that. But once you do, you get to the well-known results of Coulomb's law. So I'm going to leave it to the reader to do all this, because that's not critical. But what is critical is that when you see this e to the I kr, that is a wave that is leaving the system. And the e to the minus I kr is a wave coming into the system, entering the system. So Richard Feynman created a whole bunch of what they're called Feynman diagrams based on this. Now, the Feynman diagrams are just a way to stop writing massive amounts of equations to solve the scattering matrix. So we can just draw it first and then write the equation and then solve the equation after, instead of trying to figure out what the equation is by using his Feynman rules. So what I've done is I've just drawn a couple of these things and what they mean consequent, what are the consequences of these things? Oops. Oh boy. So what I have here is the self-interaction energy. So essentially you come along, these lines that are straight are electrons. They're just hopping along in time. And this E to the IKR1, if you can see that, that is something leaving, boop. And then E to the minus IKR comes back, boop. So it conserves momentum. So essentially every single point where there's a vertice, momentum is conserved. So you lose some momentum here, you gain it back here, and through time, in this axis, time is to the right, there's no change to the system at all. That's how you interpret the Coulomb self-energy. Now we have to note that none of these diagrams represent Cartesian coordinates, which basically means as I have particles come in, they interact and they come out. That's not on an XY plane. It's actually on a very strange spatial time plane. So for example, the Coulomb interaction, Q1, the particle comes in, it emits what's called a virtual photon. So the Q1 does that. Oop, geez, I keep typing that. And the second particle comes in and it captures this virtual photon at R2. So you have the R1 minus R2. So you have the outgoing wave here and the incoming wave here, and then they go about their businesses. So it's like, so two particles, when they perform this Coulomb interaction exchange, it's like two ice skaters holding a bowling ball. One ice skater throws the bowling ball, the other ice skater catches the bowling ball. They slide on the ice, but they conserve momentum. The total momentum is conserved for the system, but they do this through a virtual photon. So in physics, all of the interactions that we are interested in, whether it's bosons, leptons, muons, kaons, every particles go through different interaction physics. The ones that deal with the virtual photon we call quantum electrodynamics, which kind of encompasses most of the particles that we're used to in everyday life. When you go to higher energy physics and you're talking about ripping apart protons from the nucleus or that kind of strong interaction, those are different particles and they would have different physics. But for the lower energy scale, particles interacting with charges and fields and so on, the virtual photon is the mediating particle. Now, it's not a real particle. You can't find it. You can't look for it in nature. But mathematically, it looks exactly like a photon. It has a couple of differences, though. It has, oh gosh, keep doing that. The virtual photon does have energy, has momentum, but it doesn't have spin, so it's not a real photon. But it is mathematically very similar to one, and that's how we explain interaction between charges. And when they did this years ago, 50 years ago, whenever they performed this interaction, they realized it was an exact solution. So it explains everything that we know about two particles. When two particles exchange charge, they can either attract or repel, and that's it. There's nothing else two particles can do. So why go further? I haven't seen anyone go further than that. There was no reason to. It's not just an appropriate, an approximate solution. It's actually an exact solution. So why would you go further? There was no physics out there to suggest that you needed to go further. There was no other phenomena observed until now. So now, with the Exodus effect, we are showing you that if you have two particles, there can be a net translation of both of them in the same direction. A force, if you will, from somewhere. So that's why we decided to go further. What are the higher order terms that are lower in energy? What are they? We think they play a role in what we're seeing experimentally with the Exodus force. So we went on to the third order perturbation. So for this, You start from 0, you go to state K, you go from K to K prime to K prime again. You sample all of that space, and you go on and you try to figure out what is your lowest energy in that case. So for the first order, this is basically your magnitude, roughly, of your coupling. The second order is magnitude coupling that we just did, and the third order magnitude coupling right here. Each one of them is increased, or decreased, I should say, by a square root of alpha. Alpha is 1 over 137, so you're losing about 0.08 in magnitude. So it's a square root of 137, which is 0.08. So it is getting weaker, much weaker in these higher order terms, but there's reasons to do this. Okay. So unfortunately, when you do the math, you get this awful nightmare, which I'm not going to read off to you. It is awful. So instead of 4 terms, you now have 12 terms. And we're going to explain what these terms are, but we're going to do it graphically. So you have single charge terms. These is force proportional to essentially Q1. It's cubed now, and it emits a virtual photon. Q1 can also absorb one, which didn't happen before. Q2, Q3 can emit one. Q2 cubed can also capture one. That was not available before. So we're going to talk a little bit more about that. We also get the same coupling-like terms that we did in the second order perturbation theory, where a virtual photon is emitted by one of them and captured by the other. That still happens. There is a higher order term in which one of the Q's is squared. Instead of Q1, Q2, you have Q1 squared, Q2, Q1, Q2 squared. So you have, these are smaller in value because Q is a small number. Squaring it makes it even smaller. But we still have 4 of those terms. The interesting ones, though, I think, are the coupling terms, where we are mixing the Q's with the photons that are being emitted. Because when one emits, the other one goes to the new momentum too, but it doesn't actually get captured by the photon, the virtual photon that the other one emitted. So in this example, I draw Q1 emitting one. The R1 tells you that the Q1 emitted that one. Q2 just doesn't do anything. It just follows along with the momentum of Q1 because they're physically attached. The same thing here with Q2, Q1, and Q2. You are coming along, Q2 all of a sudden emits, but it interacts at R2. It escapes the system, but the entire system together has a momentum exchange. Same thing with Q1, Q2 squared, incoming from R1. So Q2 is getting incoming from R1. And the same thing over here from R2. So you got incoming and outcoming momentum. What are these momentum? Now, in QED, if you have enough energy, you are actually dealing with real photons. So if you're dealing with Bremsstrahlung, Compton scattering, Raman, you are actually dealing with real photons. But these are the scalar photons, the virtual photons. Most likely, though, they're probably just the external field. Kind of written looks like this. So you have a charge coming in, has a momentum P1, and then it comes out with a momentum P2. And it can interact with an external field, which is drawn by this X. So an external field can come in here with this, looks like a photon, very similar to a photon, with momentum K. And K is actually the actual difference of both of those momentums. And the form for this Feynman diagram is very similar to the form we already have for our scalar photons. So it's most likely, my bet would be that these are just simply the quantized electric fields. One thing that's nice about that is this tells us that electric fields possess momentum, even on the quantum scale. So we don't think about electric fields possessing momentum, but we do know classically static electric and magnetic fields do possess momentum, even at 0 frequency. So we can get momentum in fields. We also can get momentum in quantized electric fields and magnetic fields. So that's where you're getting momentum from. And these quantized fields come from the vacuum. So in third order perturbation theory, for our exodus pressure force that we see, if we have a charged plate here on one side, and say we have a positive or negative E field to the left of it, let's say it's being generated by whatever charges are in there. So in this example on the left, we have Q1, Q2. In this case, we have Q1 emitting or capturing an incoming virtual field, I guess it would be called now. The same thing with all these other charges that are happening here. They can absolutely get momentum coming in to hit these charges. That's what these terms are. The same terms on that left side where the field is, they can also emit and talk to the field that it came from. So these are also emitting field on the left side of the plate. In both cases, the force is to the right. So wherever you have a non-zero, I guess you would say these electric field amplitudes, quantized amplitudes, you would have a force in the opposite direction. The momentum would go the other way. So you have a recoil, if you will. It's a quantum mechanical one, but it's there. And that's how we would explain our electrostatic pressure force. So if we make a field and we make sure that it acts on charges, all we have to do is make sure that we have the field in a location where it's asymmetrical. And we can easily do that. So I just want to remind you, we haven't done all the math completely, but our charge we get from Gauss's law, epsilon naught EA, Q squared is epsilon naught squared, E squared, A squared. Pressure is epsilon naught E squared. So the electrostatic pressure is the square of the field times epsilon naught, and our force is that times the area. So that's how we get the classical versions of our forces. But quantum mechanically, what's actually happening is these interaction terms from these quantized fields are the ones doing, transferring all the momentum. They're the ones doing the work. So final notes here. The energy of the system that we found is lower than the second order by a factor of square root of alpha. We knew it would have some proportion to alpha. It was kind of interesting that it was square root of alpha, and it turns out that that kind of matches the number of charges. So for each order, you have an interaction charge. So you have first order is 1 charge, second order is 2 charges, third order is 3 charges. Every time you add an order, you add a square root of alpha. The selection rules, this is very exciting, for the creation and annihilation operators is now +1 and not -1, as it is in the second order. What the heck does that mean? What that means is you put a ton of energy in there to get your 2 charges in this system. So your energy is way above the vacuum energy as it was when you started. But now, because you're looking at the third order is energetically favorable because it has a negative component to it. So basically, you're coming out from 0, you're putting in your square root of alpha energy in there with your 2 charges, and even Q's, which we haven't talked about. You're putting in your charge energy in there, your Coulomb force, whether it's attractive or repulsive, it's there, it's very strong. And then you also have this other component that's a little weaker, but it's there, and it's a little negative. So your system will try to find ways to get to lower energies. The third order allows you to get to a lower energy state. So systems will naturally want to get there. This might be a way for them to do that. The fourth order doesn't show anything new. I've done the math for that. It's horrible. I don't recommend it. But it does show the same things as the second order, where you have particles coming in, they're captured by the first particles. So the momentums are all encased. There's nothing leaving the system. So there's nothing new with the fourth order. There's a lot more to go. We have to solve this equation. So when we do the graphical terms, this is what we have to integrate them over. It wasn't nice like it was in the second order, where it's just 1 over k squared. If it was, this would be just 1 over r, and we would be done. But it's not. It's 1 over k to the 7 halves, and it's this mess, which is a gamma function, and it's horrible, and I don't recommend it for anyone. So if you if you really want to torture yourself, you can try to figure this out. I had my students on it; they did not enjoy it. So, but that's something that has to be done in the next few months or something. Then we have to compare the results to the thousands of experiments that Drew has been doing, because we have a lot better resolution now on the physics and on the math. We got to compare. That's going to take a lot of time. And then once we do that, we write up a paper. So that is where I am at, Tim, for theory.
Wonderful. Charlie, thank you so much. Let me bring everybody in. Okay. And we have we have Charles Buhler with us, but he apparently cannot connect. He doesn't have his device connected. So I've got the guys. Guys, before anything else, let's put our hands together and give an enormous applause to Dr. Charles Buhler. We recorded that yesterday, and I'm going to recuse myself. I've been disorganized because I've been doing podcasts and science stuff all week, and so I'm like right at the end of caffeine. It's one of those. It's tapering off. But again, I appreciate having you all here, and we'll just keep things kind of loose and raw today. I'm going to give Charlie a moment to see if he's able to get connected. But yeah, do you guys have any discussion points regarding that?
Tim?
I mean, do you want to do Q&A?
Maybe while we wait for him, Drew could kind of do some show and tell of his stuff. While he's doing that, if other people have like questions or comments.
What Drew is, for anybody who doesn't know, everybody in this conference should know, Drew is the colleague of Dr. Charles Buhler. And so Charlie is doing the math and Drew is doing the hands-on, and Drew has done a ton of hands-on, thousands and thousands of iterations and hundreds of thousands of dollars that he has spent of his own bling. Drew, go for it, sir. Yeah, Al?
Sure. I'm going to go ahead and do a presentation, Tim, or take the screen. Or
yeah.
whatever.
Yeah. And then if it's okay, Al, is it okay if we go to yours in about 20 minutes?
That's okay. I have only a question for Drew.
Sure.
Okay. I sent to you, Tim, email about what I saw in one of the videos that Drew explained that he has problems with the repeatability of his experiments. So, did you receive this, Drew? Did you see this email?
I'm not sure.
No.
Why don't we come back?
Okay, wait. I'll make it short. You use polymers that have a very high outgassing that could influence your experiments. Okay, that's it.
Yes.
Yeah. Okay.
Yes. To answer that, the configuration that we have. Let me throw this up real quick.
Yeah, go for it, Drew.
I'm just trying to figure out which of these buttons to push. I don't see anything that says share screen.
Yeah, I'm actually having the same issue today.
Screen share. This is.
Oh, so if you do, so press the present button and then share screen.
Yeah. Also share system audio. Okay, so
there we go.
No clue. So good. Okay. So the reason I don't worry about outgassing is because we measure. This doesn't go on there. Okay, so we do not measure the. We don't measure the forces on any given piece of plastic. This is the test rig. This is the new second generation test rig as it's sitting in the vacuum chamber. And this whole thing right here, this whole plastic thing, is an ITO over PET Faraday shield box. That Faraday shield box is mounted on a frame. This is a structural frame that the thrusters are on, the electronics are on, the high voltage systems, a couple of other things, data communication, all kinds of mischief is on that thing. All of that is surrounded by an ITO box. The ITO box negates any electrostatic forces from getting outside the box. It also kind of eats the physical parameters that the box was made up of, eat any internal thing. So if I had an outgassing, I would be spraying gas theoretically from one place in the structure onto another surface. Doesn't really matter what the direction is. But I measure my forces. This is the force meter. This is an omega force meter, accurate down to probably about 0.1 millinewtons, a little lower actually. And there's a string right there. It's very difficult to see. Oh, I can blow it up. There's a string right there. Yes, it's a string. And it's connected to the center of this structure. And this structure is connected to the structural frame, not any given piece of plastic in the system. So when it's time to take a measurement, whatever's going on, this is a teeter-totter. This is a teeter-totter. This is the hinge point of the horizontal pendulum up here. That's the hinge line. And down here is the center of thrust of the thrusters. This is the center point of the thrusters. So when I take a measurement right down the center line of the thruster, but as attached to the entire structure. So if there's any stuff in there pissing gas or discharging vapor or doing all kinds of mischief, it doesn't matter. And to prove that, I had a horrible outgassing event happen to me last week or 2 weeks ago, when I noticed that some flux that had been used to repair an electronic problem got left on the circuit board and decided to outgas and fill the entire inside of my ITO box with a weird little slime that was beautiful, but was very sad because I had to tear everything apart and clean it all up and put it all back together. Curiously enough, during this whole outgassing horrible event, the test data didn't change. I ran a perfectly acceptable thruster, and it produced the thrust exactly the way it was supposed to. So, outgassing aside, I mean, it did make a mess of my structure. It just doesn't have an effect. So, I hope I answered your question.
Thanks.
Yeah, and thank you for putting up the test rig as well.
Yeah, that's the test rig, and let's see, I'm just going to throw random pictures up.
Yeah, and it looks like Charlie is still having camera issues, and that is, they made some updates to Google Chrome this week, and that is causing me some bugginess. I think it's affecting everybody.
Just trying to find something I can put up there without getting an angry letter from my lawyer. I guess I can put this up there. This is another shot of the test rig, and over here is the force meter, and it would attach to this frame right here, and then in here, inside these white frames, these are just spacers, and the thrust plates are inside of here. So there's 4 thrust plates in series, and this is just a gap. There's nothing going on here between this point and the ITO wall, which is just it's another way of saying Faraday shield. So Dr. Charles insisted that this entire structure be wrapped inside of a Faraday shield. And we went to Faraday shielded testing probably 8 years ago and never looked back. We've never run a single test without a Faraday shield because the electrostatic forces of this propulsion system are orders of magnitude greater than the asymmetrical electrostatic pressure forces. So you're instantly going to see Coulomb attraction to something. And I don't know what that is, but you're going to see it. And it's instantly going to be an order of magnitude or more above any thrust that's created, any real thrust that's created by the system. So by grounding all of this plastic, obviously the ITO is conductive, grounding all of this Faraday shield, the frame, everything's all grounded to the chamber walls, there's no more electrostatic attraction. And all the high voltage is now generated inside of this setup, and all of the low voltage that comes in is like 5 volts. So I'm not real worried about electrostatic attraction of 5 volts in a system. So that all seems to be working.
Yeah, and Drew, if I could jump in, one of the things that you have, yourself and Charlie have, that other folks don't, is incredible credibility, right? And a lot of that is from the careful, rigorous work that you're doing. You're shielding against electrostatic effects, shielding against electromagnetic interference. You are basically using hard vacuum to ensure that ion wind doesn't happen. And then you've done a bunch of other things as well. For instance, dropping the voltage down on your test apparatus to further ensure that ion effects are not dominant. So there are so many things. I mean, there's what I mentioned, as well as a ton of additional stuff that you guys have done. And again, that gives you the credibility. And I think that is why, as I mentioned to Charlie, that debrief article, they mentioned you've had over 1 million views on that article. And we've had hundreds of thousands of views of the video that we recorded last year. That's all
awesome.
Your hard work.
Thank you very much, Tim. This is an example of it all working the way you expect. Now, this is plate number 110, 111, and 112, which tells you that since I started the plate numbering system, I have manufactured 112 test articles. I started doing the numbering thing about 2 months ago. I test them 4 at a time. They're usually the same design. For plate 109, it shorts out at about 7,500 volts, so I stopped. I didn't use it today. But this is about the 12th or 15th time that these plates have been run, so their performance is starting to degrade, not because the plates are deteriorating, but because there is so much packed up thrust in these thrusters that 9,500 volts just isn't enough energy to pack more thrust in them. These thrusters, when they're turned on, are making about 6 millinewtons of thrust already. All 3 of these together combined are making about 6 millinewtons of thrust. They're also when you turn the power on, they begin to make a little more thrust than they're making when they're in their off state. So there's a pretty significant thermal gradient because it's 101 degrees out in my shop today, out there right now. So there's a pretty significant thermal gradient to the system. So for example, I turned on the unit, I don't know when this was, whatever, just around noon. So in the first 500 seconds or so, it did this. This is just the system with whatever latent, whatever is going to happen, the thermal charge, the thermal gradient, the whatever's trapped in the system still. And then I switch on the voltage. That's what this red line is, the voltage coming down. This is like 4,500, 55, 65, 35, 800, 9,500 volts. That's what the red line is down here. And you can see we're using up a little bit of current to charge up the capacitors. But the average noise, this is a very noisy current, but on average it uses about 0.1 microamps at 9,500 volts. You can do the math to get the wattage. 99% of that power is the power supply sucking that up, or a little bit of losses in the system due to some plasma being generated or something. None of that's being used by the plates to generate the thrust. But with the power on, you can see there's a little delay. I think that's in the software. I haven't figured out why there's a delay in that. But this is fairly new software, so I got to figure out all the bugs in it. You can see that the thrusters begin, it's a cumulative. This is all 3 of the thrusters on at the same time. it works out to be around, I don't know exactly what this test is. It's about 600 plus whatever the delta would be. That's probably 2,000 micronewtons of thrust in 2,000 seconds. So that's about 1,000 micronewtons of thrust per 1,000 seconds, which is about 330 micronewtons of thrust per thruster in 1,000 seconds, which is about what these thrusters do. I have lots of individual thrusters doing individual thruster things. Like, for example, this is one of the thrusters, one of the three doing its thing earlier in the day, maybe. Yeah, it's a 9:35 in the morning. So this is an example of, yes, you can put three thrusters together, turn on the juice, watch them do their thing, turn off the juice, which is right here, this red line. This means going back up to 0 voltage and just, tapering out. And the thrusters stop making extra thrust and go right back into the drift mode. So this is an example of propulsion on and then propulsion off. And for the astute among you who can, I got no way to do this digitally. But anyhow, if you look at this slope right here, this slope is pretty significant. This slope here, which is this is a power off slope. This is a power off slope. This slope is much less than this slope. So what that tells me is that when I ran this thing for 2,000 seconds, it packed a little more thrust, a little more charge, which is going to produce thrust, into the plates, so that when you cut power, the free electrons, they're gone. But the bound electrons, or the bound charge that's in the system, that's going to continue making field, whether you want it to or not, is still there. So I'm actually making thrust. I'm making more thrust on, this line has a shallower slope than this line. So, you do this 8 or 10 times, and the thrusters are just on. Like I said, there's about 6 millinewtons of thrust, or 5 millinewtons of thrust inside these thrusters. So that's the kind of stuff I do later on in data reduction, and I put together some pretty charts and stuff, just to show myself what this design is doing. And that's how I optimize this particular design versus the last particular design. And then, I run all this stuff by the gang and see if anybody's got any comments on it. And that's what Charlie and I do. He figures out the physics, and I do the experimental data analysis and collection of information that, he does whatever he does with it, because nobody actually understands what he's talking about.
Well, and Drew, thank you so much. We are just about at the top of the hour. So I do want to go to Al, and I want to try and kick off his presentation at 1. Again, he is overseas, so it's super late his time. I should apologize to everybody for being disorganized. As you can see, I did actually get my camera working, so at least one thing is fixed. I'm just going to keep, fixing things as I go today. It's one of those. It's like we're going to put duct tape on the wings while the thing is in the air. But Drew, thank you so much. And if you're still here later, I would love to have you share more about it. And I do want to do a podcast drill down interview with you as well. You keep dodging me, but so guys, let's put our hands together one more time for Dr. Charles Buhler. And again, I am overjoyed at the work you guys are doing. I mean, it's amazing is an understatement. Amazing is an understatement for what you're doing. So, okay. So what I'm going to do is take everybody out except for Mr. Baur. Al, welcome, sir. And let me see. It looks like you have 2 presentations that are uploaded. And oops, you're muted, sir. There we go. Okay.
This is my screen.
Yeah, that's your screen. Is this the one that we should start with, sir?
Okay.
And if I could preface this a little bit for you. So you came on before, you have shown some amazing videos. I'm not sure if any are embedded. They probably won't play from screen share, but if we can almost walk you through sharing those as well. So again, what Drew and Charlie are doing is not ion wind. What you are working with very much is ion wind, at least what I've seen in the past, your past work. And that is not negative in any way. You've done some amazing stuff. You've been able to suspend a levitator in between these basically high voltage polarized emitter and collector, which is unheard of. I mean, so that it's remarkable.
Well, it's only one now. There is no grounding now.
So even better. Well,
Yes.
let me take myself out, and it's 1:01. So again, apologies for the delay, but I will be here if you need me.
Okay. Imagination is more important than knowledge, for knowledge is limited. Where imagination embraced the entire world, stimulation progressed, giving birth to evolution. Albert Einstein. Imagination is the spark, motivation is the fuel, together they create the fire. Without imagination, motivation may lead to hard work in the wrong direction. Without motivation, imagination remains just a dream with no execution. Charles Buhler. Now, what I'm going to do in this podcast, it's different from what happened before. When I started to write this and my son saw this, he said, you can't do this. It was full of formulas, and he said, nobody will be interested in this. So I took most math I took out, and I put some more creative things inside, and I hope you will like it. Now, I have to see.
Oh, yeah. If you put your mouse over it, there is a back and forward button. My apologies for interrupting.
Okay. In this session, I like to share the evolution and experimental advancements of electrostatic levitation, as well as my personal motivations behind this work, so that more people can experience its magic firsthand. It's open source and offers the lowest cost among all existing levitation with propulsion technology. The danger of using high voltage is low because the current limiting. Okay, now I have to go back to here. Okay. What I'm going to explain is double cylinder, why it's stable. The last time when I was talking here, my knowledge was limited, and now I know exactly why the double cylinder is stable. And okay, then I show the 3-cylinder levitator, per levitator with the highest efficiency, and I will explain what the meaning of that is. I start to use PLA wire to connect the interconnections of the levitators. Okay, I will show you a crossroad in video, which I wasn't sure that it would work. Then I built a prototype 2, and in the meantime, I'm working on 3. Invisible wall, very important. I will show you a video and give you later explanation, because the invisible wall is part of my motivation why I started this. Then inverse electroscope with tensor technology, also video. Investigations and problems in the Biefeld-Brown wireless levitator and my look on this. Okay. What is a double cylinder? You see on the right lower part, you see the blue is where the high voltage is. And below you have the corona. You see that 7 degrees is pointed inwards. And this is because the electricity will try to find the easiest part to get to the ground. Okay, and the same on the other side. And this is the secret of the double cylinder levitator. It's pulling up here and it's pulling up on the other side. And this will keep it stable. Okay. Okay, you see on the left, you see an enhanced picture of the corona, and below you see 2 ionization points. You see that corona is much more stronger than the ionizer points. Okay. Here you see it more stronger. Okay. Now I give here a definition of what is corona and what is ionic wind for somebody that wants to see this. And the explanation why the corona gives more light than the ionic wind is because it's a bunch, it reacts with a larger amount of air molecules. Okay, the 3-cylinder levitator. What is special on this and why I started to make it, my idea was if I put a cylinder in between, the static field that will be produced on the cylinder, on the middle cylinder, will push the corona outside. It didn't happen. It didn't happen. So what did happen was that the levitator started to go up and down, like, how we call it, Benjamin's bells. But what happened, I squeezed the middle cylinder. By doing this, because of the interconnection, the outside cylinders get bent inside, and then it became working more exactly. Okay. Now there is on YouTube, there is a video, so I can't put it here. And it is possible to see, you see below here, under the name from UFO to IFO. Okay. Now, what is interesting on the pair levitator, when I started to push down the lower part of the cylinder, I got a better result. So the reduction in the energy reduced from 450 to 240 milliwatt, and it's able to carry between 30 and 40% of its own weight. The distance of the ionizer below is the closer it is, the slower it goes. The farther away from the body, the faster. Okay, I use PLA interconnections that gives more robustness, but also I use it for in the rim of the levitator, which make it much more easier to build these. Okay. Okay, here I have a drawing for somebody who wants to build a spare levitator. This is the side, and this is the other side. Okay, if you look at the circle in the ionizer, it's for mechanical reasons and also for to have a better electrical contact with the levitator. So now I try to understand what is the difference between the cylinder and the pear shape. So I made a simulation on electrostatic program, and it didn't give me a clear answer. So the reason that I think that the pear shape is much more effective is because the capacity in the cylinder on the upper side and the lower side is nearly the same. So it is attracting to the upper charge plate and also attracting with similar force to the ground. By making it pointed, this change. I don't know if this is the reason, but this is what it looks to me. Okay. Now here you see that the how it looks like, and the interconnection is with PLA. Here you see two charts. The one is with 2 ionizers and the other one is 4 ionizers. With 4 ionizers is much more noisy, and the cycle that you see, for example, in the 2 ionizers is the circle of the trajectory, and because of not the charge is not the same on all places, so you get a repeated cycle that looks something like that. If it would be a good built, symmetrical built trajectory, it would be nearly flat. Okay. Here you see example of the PLA. Okay. Now the crossroad. So I will try to activate the, let's see if I succeed in this, crossroad. There's no grounding. It's on a wood table, painted wood table. When it's in the middle where the crossing, it goes faster because the field is stronger there. Okay. Okay, the next one. Okay, battery prototype 2. The prototype 2 is more wide track from 40 to 60. It has a fast charging option, more clear indicators, removable high voltage connector, trajectory height is locking. It's possible to lock a stable base, easy to assemble, levitates large objects, coating. Top of the screen is matte black, preventing reflections. Okay, now, okay, so I will show a movie about that one.
And Al, I'm sorry, are you trying to show a video? Because it's just showing the battery prototype 2 improvements.
Yes, you don't see it?
No, because you would need to share that separately.
Oh, okay. Okay. Stop showing. Okay.
Yeah, so for videos, you can share the videos in a browser window, or you could share the video. If you go to present, click the present button.
Present, okay. Video file, okay. So I have to upload it.
Yeah.
Right. So I need. You didn't see the crossroad?
No, because it's only sharing the one screen.
Okay.
Okay, now I can bring it in. Thank you, sir.
Okay.
And
there's no grounding here. Okay, no ground plate. It's on a wooden table with paint. When in the middle, it goes faster. Okay.
okay,
so
and I'll put myself back in. Do you want me to put your presentation back up? Let me add that back in.
I want to show the movie from this prototype.
Okay, if you want to upload that, I can put that on the screen for you too.
Okay. Remove from playing picture. Okay. Remove.
There we go. I see something working.
Video, and I need.
Okay, so I have battery pair. Oops. Yes.
Okay.
Wonderful. Al, thank you. That was an amazing video. Let
Thank
me
you.
put that one back up.
Okay.
Yeah, and again, let me know if you need me to switch slide shares for you.
Okay, we finished this one. Okay. Now, the invisible wall. I was working in a factory, a polymer factory, and they made polypropylene and polycarbonate sheets. And under certain conditions, there were very high voltages because they was acting as Van de Graaff generators. And one day there was a cloud drifting. Let's see. Okay, you see it on the right lower place. So you see the cloud, but the action where the spikes were, they were between 18 and 20 meters. The electricity was built up here, but the invisible wall was not near the extruders. So I don't know how to explain everything, but what I can tell you that it is real, and it shows that it's possible to stop heavy objects. In the movie, on the end, you will see a trajectory, and which is made from two half circles, and where there's the connection of the circles, there's a change in the field, and this creates an invisible wall. So what is interesting in this video, that if you go the opposite direction, the levitator will go faster at that point. Okay. Now, according to Coulomb's law, the voltage required to stop a human body with the height of 186 and the mass of 76 kilograms, you must exceed 3.5 megavolts. Okay. Okay, I will show now the movie. Tim, can you show the movie?
The invisible wall. For over 20 years, I worked as an engineer at a plastic factory in northern Israel. Repairs, electricity, programming, nothing prepared me for what happened one unforgettable day. It started with a phone call from Musa, one of the machine operators. His voice shook. "You have to come now," he said. "There's an invisible wall. I can't get to the polypropylene area. Minutes later, I was racing to the factory on my scooter. When I arrived, Musa stood there pale and trembling. Together we walked to the production line, and then it hit me too. Something was blocking me. An invisible and strong force, like a wall of flexible cushion, pushed me back. I wasn't imagining it. My full body simply couldn't move forward. Then just as suddenly as it appeared, the wall vanished as if nothing had happened. 2 years later, it's happened again. Same place, same eerie force. A blazing hot summer afternoon. Before and after the incidents, we saw strange signs. Thin, sharp sparks jumping beneath the plastic sheets. No discharge to the ground. The air was dry. The static voltage climbed to unimaginable levels. Millions of volts. After I retired, I couldn't let it go. I built devices, experimented with high voltage, and somehow I cracked something. I made objects levitate, breaking rules physics swore were unbreakable. Was the wall an accident, or was it something bigger? Something waiting to be discovered.
Al, thank you again. That was amazing. Okay, let me take the video out. Should I put your slideshow back up, sir?
Okay. 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 Okay, I want to give here a more technical explanation. The horizontal spikes measured between 18 and 20 meters. The spikes were below the corrugated polycarbonate sheet. The spikes were very thin. The height between the ground and below the plate is about 1.2 meter. There was never a discharge to the ground. The wall was not near where the spikes were produced. I explained this before. There was no sensation of high voltage when I was in this invisible wall, such as hair standing or sparks or things like that. In the time that I worked there, it happened only 2 times, and I was working there more than 20 years. It is in my belief that there was a very high charge air and invisible charge cloud within the cloud. There were 2 different potentials that created the wall. Conclusion: with low humidity of 3000 volts millimeter, over 20 meter translates to 60 million volts. According to Coulomb-Verse square law, around 3.5 megavolts is required to generate this force to stop a body of 76 kilogram. Okay. The significance of the invisible wall lies in its ability to influence heavy objects. However, there is no evidence or theoretical basis suggesting that the Biefeld-Brown effect can function in space. Convincing organizations to invest in a costly space experiment without proof is at best extremely difficult. Testing in a vacuum chamber is also problematic due to interference from the chamber walls. Even in NASA, where they have a very large vacuum chamber, the walls can interfere with the experiment. The best possible place on Earth to make the high voltage experiment is where humidity is very low, no wind. Still, I believe that one day we will harness the electrostatics in space for propulsion and protection. We simply need to discover the exception within the existing scientific principles. Okay. So here I have some suggestions. So how to make very high voltages. There, in principle, there are a couple of options. One is the Van der Graaf, who is relative low cost because you don't need large in the way of width, because you need low current. Other option is a Pelletron, which is expensive, and it's not that simple because money is never there. Okay. Okay, inverse electroscope with tensor. In my search for a truly non-intrusive voltmeter, something that in principle doesn't exist, since all the measurement system requires some energy. The tensor offers a cost-effective and minimal invasive solution for monitor high voltage environments, including air pressure, temperature, stability, humidity. They connect to the high voltage line inductively, ensure minimal interference. For optimal performance, use 2 or 3 interconnected loops that I will show you in a video, maintaining the width between a 6 and 10 millimeter. Okay. Now, here you see below you see the picture of the red copper, and the red copper has 2 big holes. One is for the high voltage output that goes to the trajectory, and one which has no connection is for to put the inverse electroscope, which is made from a straw, and inside is a tensor as connected on top of the straw, moving the tensor. It's a good indicator for the show voltage stability. Everything that happens there, never mind if it's air draft, humidity, or leftover charge after closing the supply, you can see everything very clear. It opens a new door for experimental 3D structures. So interactions is inductive and the load is high. The load on the high voltage is low. Okay, let's see the movie. Present video. And so that one. Tim, are you there?
Yeah. Sorry, it's not letting me. Why is it not letting me remove that? There we go.
Okay.
There we go. Okay. Yeah, again, weird technical issues this week, but my apologies.
Okay. Now, tinsels are not something new, but in my case, it is very useful for seeing what is going on with my voltage. In principle, it doesn't matter if it's 30, 35, or 40 kilovolts. I want to know if it's stable, if I have leakages, or something else is going on. And which this way, with the tinsel, I can see very clear what's going on. So really, truly non-intrusive voltmeter, it's problematic. So the best is to use 2 or 3 interconnected loops, circuits, like in the video, with a width of 6 to 10 millimeters. Investigating and problems with the Biefeld-Brown wireless levitator. Okay, this is what I'm starting to experiment with. If you look the red and the green, the ionizer is pointed vertical. It means that it doesn't move to the left and not to the right. Now, by putting an asymmetrical capacitor, I hope to be able to move it. And what you see, the blue, the upper part receives energy from the charge plate, and the little part of the capacitor has the other polarity of the voltage. Okay, this is all that I have to give, and I want to thank you. So that's it.
Al, thank you. Thank you. So let me do this. Let me see. Let me take down that. I will bring everybody back in. Let me see who else. Well, we have Matthew wasn't really here. Okay, so I guess it's just us. John is hiding somewhere, but I don't see him. So guys, let's do this. Let's put our hands together and give Mr. Al Baur an enormous applause. Al, my apologies again for the technical issues. I'm having all sorts of weird bugs. I'm having buttons that won't push or unpush, and my camera wouldn't connect. I'm having spotty connectivity. There's just, I don't know. They did a big Google Chrome update just recently. So
what about the time? It's supposed to start more 4 hours from now.
The APEC?
Yeah.
That would be the open mic, but the conference is always at noon Pacific. So yeah, so that could just be a timing thing. Yeah, and you know what? Let me bring Matthew Szydagis in. Matthew is back.
Oh, I was here the whole time. I just was conserving bandwidth. My internet is terrible at home.
Okay, yeah. Okay, well, no problem. I can pick you out if you want.
I've been listening the whole time to everybody from the beginning. Yeah.
Well, do you guys have questions for Al?
Oh, no. I thought I'm on it. I'm on in 20 minutes, right?
Yeah, I do.
I should stay.
Yeah, Drew, go for it.
I'm still trying to figure out there's no batteries or anything in the little teardrop shaped things, right? It's just 2 pieces of teardrop shaped things on a frame.
Say it again.
Okay, the teardrop shaped thing, the thing that.
Yes. Okay, I call it the pear shape.
Pear shape. Okay. Are there is there is there batteries or anything, or is that
No,
just
no,
electric?
no, no, no,
No batteries.
no.
Okay. So the
Okay, I'm explain you in the way you understand the world. There is a electrostatic field above the levitator, so it will be pulled up. Because the ionizers on the lower side, it will reduce the voltage on the levitator, and it will stabilize somewhere in the middle. Is that clear? No.
okay, so what's stopping them from just pulling? Is it Coulomb attraction? Are you
Okay.
electrostatically attracting the pear-shaped thing to the thing above it?
Okay. When it will be attracted more, there will be more ionizing on the lower side, so it will go back. That's the way it stabilizes itself.
Really?
Okay.
Okay.
Now, what is more?
So
I
let's say it didn't. Let's say the ionizing thing didn't work. Would it just rush up and you know those
yes,
things?
yes, yes. I think it will stuck on the plate. Yes, and yes.
And then they'll
Yeah,
be
but-
both at the same potential, and once that happens, it'll just fall.
No, you know, if you don't have an ionizer, it will work as as the bell from what's his name, Benjamin Franklin. You know the bell of Franklin, Franklin's
Uh,
bell. Do you know about it?
uh,
Well,
yeah, there's like electrostatic ding 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 ding.
yeah, exactly. Okay, now if you have, let's say, a circle with no ionizer, it will be pulled up. It will get the same charge as the plate, and then because it has the same charge, it will be pushed back.
Right, it'll be fall
And it
off.
will be attracted to the ground. Okay, so it goes up and down, up and down. And the ionizer eliminates this.
Yeah. Well,
Okay, so you're saying that the pointy end, the end down here,
Yeah.
that's emitting corona. That's going into corona or something.
No, the corona is on the upper side. The
Oh, it's on the upper
ionization,
side.
yes, the ionization is on the lower side.
Well, what are you calling ionization then? Corona is the discharge of ions.
There's discharge on the lower side from which ions. Yes, on one point it's a very thin wire, and ions go outside and have a pushing force. This is what pushes the levitator. Mhm.
Okay, I don't understand this at all.
Wow.
That's fine.
No. Thank you for that, because one of the things that I don't get, why so few people are interested in this. So it's more difficult than it looks for me. One of the things that I can tell you, there's now in the near of you, there's one unit with a battery unit that Charlie want to check in the vacuum chamber. Do you know about it? Oh,
What now?
Charlie wants to put my system in a vacuum chamber.
Okay.
Do you know?
Charlie doesn't own a vacuum chamber.
Marek.
Our team owns a vacuum chamber. So you're saying Charlie wants to put your thing in our vacuum chamber?
No. Marek has a vacuum chamber. Is that correct?
Mike who?
Mark. Sokol.
Mark.
Oh, Mark. Oh, yeah, that's a whole other team. Yeah, that's the Jared Yates team.
Okay, then we have Charlie.
You're saying Charles Crawford.
Charlie.
Not Charlie Buhler.
Charlie Bo?
Crawford.
Different Charlie.
Different
So
Charlie.
I mean, the bottom line is you have a corona with ion wind coming out of the top. It's going into the foil and it's pushing out the bottom. The top is attracted to the track above it because of column attraction, and the bottom is going to be repelled a little bit because you've got ion flow out the bottom, right? And that's why you've got the teardrop or the pear shape. And so it's dynamic instability, right? The same thing as that old levitator top. It's an unstable system, but is dynamically stable as long as current is flowing. The thing that excites me about it, though, is it contrasts very well with what you and Charlie are doing. And when I say contrast, I mean it is almost the exact opposite. You guys are starting with similar basic forces in terms of electrostatics. You guys have gone to a low voltage, no ion approach that is entirely based on asymmetrical capacitance. And Al has gone to a high voltage, entirely ion approach where there's no asymmetrical capacitance. So what you've done is you've started kind of in that same place in that murky B-Phil Brown territory, and you've kind of teased that apart into two different areas. And that's exciting because both of those have potential. Right now, with Al's, because it's ion based, it has like you're not going to be able to use that as easily for a space drive because it's going to require reaction mass. But back in the 50s and 60s, they did have an idea for the invisible wall. They actually thought that you could create an airlock with that. The idea was slightly terrifying. What they were going to do was basically take a volume of air in space and just charge it up to an insanely high voltage and use that as their airlock, right? So, but I mean, there are several ideas out there for it.
Drew, there's something else. I asked 4 different AI systems what happens if I elevate the voltage. 2 say that the levitator will go up. 2 other AI say it will get unstable. All of them were wrong. What happened is that the levitator goes down. Now, in the past, I didn't understand why, but now I know. Because in the moment that you elevate the voltage, the corona starts to be stronger. You get a stronger corona wind, which pushes the elevator down. And because of that, it will continue to be stable also on high voltages. This is a very interesting phenomenon, and maybe it's possible to utilize it somehow in the future. That I don't know yet what it could be, but it's an interesting phenomenon. Okay. I don't hear you.
Yeah, I don't believe in anything that comes in or out of an AI system. I've yet to see the things be of any value past generating really bad code for doing graphics. But I like the idea that your system is dynamically stable, and that is as the voltage changes or whatever, the forces are they equalize. I would think that it would get into a porpoising effect, short out and drop. But you seem to have worked out some kind of dynamic stabilization system. That's very interesting.
I just wanted to briefly add that I concur with Drew. And actually, I spent, what was it, Jared, 3 hours convincing Jared that AI is not yet ready to do cutting edge frontier research. At least it's improving every day, but it's not smart enough.
That's my experience.
Yeah.
None of our absolutely zero of our research has been based on it or use of it. Nothing.
Well, yeah, I would go with that. From what I've seen, AI is trained on what is known, and it tends to fail at what is unknown, right? Mm-hmm. So, or what is intuited also. And I've seen instances where AI actually does intuit things, but it's few and far between, and it's guesswork, and it lacks, it's not on a human level yet. So, but that being said, people like us are going to become far more rare, because what I'm seeing is, like, even in email lists that you guys are on, there are folks who have just turned to using Grok, for instance, instead of actually doing math. So,
I have found factor of 10 errors in Google Gemini in the math, where if you're not a mathematician or scientist, it sounds smart and sounds very sciencey and plausible. But if you know the answer, you realize it made like a decimal point error or factor of 2 error. That was with Gemini. I've seen similar with other systems.
I think it works better when it has more data to train with. Like a lot of the podcast interviews I do tons and tons of Google lookups, right? And Gemini is now the AI. It precedes search results with the AI, and it has a link, which is helpful. And what I'm finding is the more public and the more people who are writing about a story, the better the AI seems to understand it, I guess.
The answer, I think, to one of the earlier questions is why doesn't anybody give any money to this sort of research? Is that the world is happy the way it's happy wallowing in mud. It's happy. Nobody invented ketchup to kill the taste of rancid meat until Heinz came along and invented, developed ketchup. They still had rancid meat. They just put ketchup on top of it. Nobody figured out the meat fix problem for another 30 years. So people are just happy with whatever they have right now. They have their iPhones 26 or whatever it is. They have overnight delivery of stuff from Amazon. They have 30-minute pizza. They just don't need anything better. They don't need to go to Mars in 3.5 days. Why would they bother with that when they're perfectly happy wallowing in whatever ignorance they live in? That and the Democrats destroyed the investment system in this country. So there's always that.
Yeah, I mean, if I was gonna, sorry, go for it, Al. This is your time, sir.
I have a question on John Brandenburg. John, you suggested a gravity manipulation with a balloon and a half motor. You remember?
Yes.
Okay.
Yes, I do remember.
And I saw one of the videos that I think, what was it? I have to see. It was David Chester made the experiment. What was the result? Do you know?
He has not communicated to me the result. Can you hear me?
Yes, I hear you.
Yeah, no one has gotten back to me about any of these experiments. I just assumed they were all successful and got the same results I got. That's what I assumed. I would just urge you to do it yourself. I
did.
You did? What happened?
Okay, you want me to show you?
Yes.
Okay, so wait, I have to upload the picture.
And with the female assistant that you had earlier too.
Okay, I add a picture, balloon. Tim?
Yeah. Is it okay? There we go.
Okay, one of the things that you say that you need a frequency of 400 hertz.
That's what I used. That was
okay,
the
wait. I think it's 400 terahertz. You don't need to break a motor to make this experiment. You can use a resistor, put some voltage on it. The resistor will heat up, creates heating and the balloon will move up. So it works on convection.
No, it does not. We checked for that immediately. We checked for that immediately. We actually had a bunch of resistors in place of the little motor armature, and we gave it the same power. And of course, it got warm, whereas the little motor armature didn't. Its resistance was inductive, so it didn't get warm. But we found that after about a second, the balloon would bob up and down slightly due to thermal kind of vortices rising from the heated resistors. But you'll notice if you watch the video, the weight loss or, whatever gravity, a weakening of the local gravity field was instantaneous when we turned on the power. And when we turned it off, it regained its old weight. So I've been doing experimental work for 40 years. I mean, I'm not going to waste my time with something that doesn't work. I wanted something like you made in your beautiful experiments, and that's what I did. Now,
it would be nice, John.
Yes.
It would be nice if you give more information so we can repeat your experiment, because the information.
Okay.
What?
Yeah, I thought I provided. It was a fairly simple experiment. I just used a audio amplifier at about 30, 40 watts.
I know, but there's nothing about weight and measurement and the power that you use, nothing. No technical information.
Okay, I will endeavor to do this. The experiments were actually done several years ago. Believe it or not, I don't know. We were told not to publish them.
Well, I don't see a secret there.
What's that?
I don't see any secrets.
Something well, that's what I thought. I thought, why try to keep? Why are we're not supposed to talk about something that you can do so simply? And but I will, if necessary, I will actually rebuild the experiment right here in my apartment.
That would be very nice. That would be very nice.
Give you guys everything, every detail.
Okay.
Down to the serial numbers on the little motor armature.
Well, and guys, so we're at the top of the hour. It is 2 p.m. If it's okay, I would love to wrap things up and then take it over to Matthew.
Okay. I was supposed to talk at 1 o'clock.
Yeah, John. Yeah, sorry. Take it. Let me. Sorry, my mistake. Matthew, is that okay if so about an hour for John to talk, and then we come to you?
Unfortunately, I'm supposed to give a talk on a podcast at 4:30 Pacific time. So I wanted to.
You should let John go first. Yeah, but may I ask one quick question though?
Sure. Yes, you may.
First? Yeah. So I wanted to ask about what about do you think neutral particles could be affected, or only charged particles, by the force field?
I'm sorry. The question is not to me; it's to Al.
No,
right?
it's to Al. Yeah, I'm sorry. Yeah.
Oh, sorry.
Yeah.
Can you repeat the question?
Yes. So I've had long discussions with Mark Sokol actually about this. I don't know if Mark is here today, but do you think a neutral particle like a laser beam would be affected by the force field, or only charged particles?
No, I made it was not a high power laser. I guess if you take a 100 watt laser, it will burn out the levitator, but I didn't see any change. The same I did with ultrasonic waves. I'm sure that both ultrasonic and also laser will influence on a certain level, but it needs a high power. Okay. This answers your question?
I couldn't quite hear. Are you saying you would need to be high powered and low powered are not deflected, or the other way around?
No. If you want to influence it with the laser needs to be with a high power. So it needs to be the light of the laser will do nothing.
Okay.
But the heat of the laser could make a change.
But can you deflect the angle of a laser beam, or is it only charged particles that are deflected by the force field?
No.
If you shine a laser beam at the invisible wall, what happens?
Oh, that is what you... Nothing.
Yes. Nothing. Okay, that's exactly what I expect. Okay.
Okay. Nothing.
Yeah.
If I could comment, the amount of gravity or whatever effect. Let's assume it's kind of like you're making gravity. Okay, the amount of gravity necessary to make an observable change in a deflection of a laser beam is so much higher than just terrestrial gravity fields. Like they are, if the forces they're experiencing are roughly, the same as terrestrial gravity. So I don't know why you would expect to see any observable effect due to a laser.
I would not. I was just confirming because Mark told me he would, and I disagreed with Mark, and we argued for 3 hours. And so, no, you're confirming my intuition, because also if it's electromagnetic, it also wouldn't deflect a laser because photons have zero charge. And so, okay, right. Mark's not here to see the fact that I won the fight, it seems. But yeah, where is Mark? So I can't gloat that I was right.
I'm not.
By the way, I think Mark took his kids to the beach because he was talking about sharks.
All right, yeah.
Okay, here's one other point. If you have some kind of force field like that, you will see maybe a change in air density, and that will create a refractive effect.
Okay.
So, if on a hot day and you look like on the hood of the top of your car, and you look at grazing light beams coming across, you'll see that as you get closer to the roof of the car, you get a lot of refraction just due to it being next to the layer next to the hot metal. And I was quite fascinated by that as a child. But
those are photons. So yeah, but neutral particles in general will not be deflected like a neutron. Cosmic ray neutrons.
Cosmic ray neutrons.
The invisible wall. These are basic electrostatics.
No, I agree, yeah. But I was arguing with Mark because Mark was convinced that neutral particles could be affected too, and I'm like, no, only a little bit maybe, but not significantly to affect neutrals.
Mark should, with all due respect, Mark should show up and argue this himself.
Yes, I know. He's not here.
Well, he's you know what? He's doing a test, so he can do the laser tests and stuff.
Okay.
Yeah.
If it's
by the way, I just wanted to mention one thing, Al. Just get yourself a public address amplifier of about 40 watts and a tone generator at 400 hertz, or roughly middle C, that's about 450, I guess, and start there. And I will be supplying, where do you guys have Hobby Lobbies where you live?
Well, John, why don't we try and wrap this up? So,
okay.
Why don't we do
sorry.
this?
I'm just.
Yeah. Okay. So, guys, why don't we put our hands together?
Tim, I want to add something. For somebody who wants to see a levitator that moves an electrostatic field, it's a Mark so-called, he has a unit, a battery unit. So you can see it there.
I just want to say I love Mark, so I respectfully disagree with him. I love Mark though.
Yeah. Well, guys, let's move along. If it's okay, let's put our hands together one more time for Mr. Al Baur. Al, thank you so much. I'm sorry for being difficult. I'm just trying to kind of get things back on track. It's been a bumpy ride, but we're rolling. So let me take everybody out and go to Mr. Dr. John Brandenburg.
Here, Dr. John Brandenburg.
Let me put your slideshow up. The physics of time.
There you go.
Yeah. And again,
Okay.
John, let me apologize. It's been just like one thing after another this week. So it's like, dear Lord, please. You know,
Nothing important is ever done easily. That's because this is important. It's all important. What we're doing
I will be
today-
here. Hopefully you do not have videos embedded. They will not play. But other than that,
I learned not to put embedded videos.
I know. Yeah. And this is the future too, because this leverages Google Chrome system. So not just StreamYard, but that Riverside that I use for the podcast, pretty much like most future systems are going to be built something like this because it's using what's already in Chrome. So.
Okay.
Okay.
Very good.
Let me,
yeah, I'm going to give 2 kind of 20-minute talks. I made them deliberately kind of brief so we could have some time for discussion. I think you'll find this quite thought-provoking. I decided to make a fundamental examination of the nature of time simply because people had been talking to me about time travel, and they had been insisting to me that time was an illusion. And I said, well, tell that to your landlord when the rent is due. I mean, so I decided let's look at why people think time is an illusion and what is it actually really in terms of physics. And this, of course, a very fundamental question. So next, can I just push the button?
yeah. Actually, that was why I asked you to upload it. Yeah. So.
Okay. Here we go. Okay.
Yeah.
Okay.
Yeah.
I'm going to discuss in this talk, and I aim to do it in about 20 minutes. I'll just talk about the idea of the physics of time, what we're concerned with when we examine that. We'll talk about time as the Hubble expansion of the universe. That's one measurement of time. Time is the motion of waves. And then time is the increase of entropy. Why does your cup of coffee get cold? Why doesn't it get hot? You know, and then I'll make the proposition that time is best represented as an imaginary number, and then I'll summarize. Okay, I have approached this because of the gem unification theory, which has it is a 5-dimensional theory. It includes the idea that there is a hidden 5th dimension that is independent or orthogonal to all the other dimensions, but it's restricted in size. So really what it is the size of subatomic, roughly the size of subatomic particles, depending on how you measure their size. And like the classical radius of the electron, which is, forms the basis for the Thomson cross-section for scattering laser beams with light, with just free electrons. That acts like a real cross-section, and it gives a size of about 10 to the minus 13th centimeters, or 10 to the minus 15th meters, femtometers. So, but anyway, the gem theory is based strongly on the Kaluza-Klein model, where you add this hidden dimension, and not only do you get the equations of general relativity, but you get the coupled equations for electromagnetism to general relativity. So this is quite powerful. And it turns out without going into detail, the important number of the universe is 42.85, as it turns out. Now, this theory actually gives you an analytic expression for big G, the gravitation constant. And it is quite close to what is observed, to within about a part per thousand or so. It also gives the value for the mass of the proton. So imagine the Big Bang happens, and 1 second later, you have a universe with electromagnetism, gravity, and electrons and protons. You have a expanding hydrogen plasma in the kind of just basic Big Bang universe. No bells or whistles like inflation or anything like that. So where do we get this idea that time is an illusion? Well, actually, I thought it was just some kind of a product of some bad weed somewhere down in Berkeley. No, actually, it was inspired by Einstein. Because of relativity theory, he has space-time. So you have X, Y, and Z, the three spatial coordinates where we can move everything freely. Then there's time. And in relativity, you can basically go forwards and backwards in time however you want. And of course, an observer can see the past, the present, the future, things like this. So the idea that time was an illusion, and what he meant was the difference between past, present, and future is an illusion, actually came from Einstein contemplating the meaning of relativity, where he had formed space-time, and time became a dimension just like X, Y, and Z. However, that's not our experience. In reality, time must move forward. We cannot move freely in time like we can X, Y, and Z. We are stuck we are traveling forward in time, obviously, but we can't travel backwards, and we can't sit still. So, what is it about the time dimension that makes it so different than the spatial dimensions? And what does that mean in terms of fundamental physics? Okay, one way to measure time, we're talking big picture here, is that time is the expansion, the Hubble expansion of the universe. It can be likened to letting some gas molecules freely expand into a vacuum. You're actually stomping on the toothpaste tube, and the toothpaste is coming out, and you can't get it back in the tube. It's an irreversible action. Now, some people are saying, oh, the universe is going to turn around and collapse in on itself and have a big crunch. There's no real evidence for that that I've seen. People have been looking for that for years and years and years. They can't see any sign that it looks like the universe is right on the boundary of being open and closed, but it's going to expand forever. And that's really the limit of a bunch of free particles, kind of an ideal gas limit, expanding into a vacuum. And that expansion is irreversible. You can't put the toothpaste back in the tube. What's done is done. As Omar Khayyam wrote in the Rubaiyat The moving finger writes, and having written passes on, and all your tears will not wash out a single word, or your prayers bring back the pen to cross out a single line. Time moves forward irreversibly. And that is the second law of thermodynamics. So we have a situation where if we take general relativity, and of course special relativity is a subset of that, time appears like an illusion. You know, the idea of time as we experience it, with a past, present, and future. But time moving forward in time, experience of now, is as real as the atoms making up matter. And that, interestingly enough, is not something that is covered in relativity. Relativity doesn't concern itself with atoms. It concerns itself maybe with a mass or charge density, but it doesn't go into any detail about what that is. It just says it's there, and there's 3 spatial dimensions and 1 time dimension. And what's interesting is the time dimension picks up a negative sign. It's the difference between time and the spatial dimensions is that when you do a measurement of an interval in space-time, time ends up with a time squared ends up with a negative sign in front of it. And what that means is you can actually develop a formalism. All physics is based on formalisms. Everything from F equals ma to electric field is the force per unit charge, etc. Time apparently is imaginary. It's not an illusion. It is imaginary. And you can see that in the wave equation, just take it in 1 dimension, like a radial scalar wave. It has the waves go outward like ripples from a disturbance on a still pond. They don't come back. And they move away at a certain given speed, in this case, the speed of light. And that gives us so that time and spatial dimensions of the waves are coupled. Time is, or rather space is time divided by c. So time marks the spreading of ripples on a fluid. That's an everyday example. Now, people find the imaginary number a little frustrating. I know I did, because it's a cipher. You think, well, okay, you square I and it gives you -1. You know, something that's not supposed to be possible based on, you know, it's like imagining the Pythagorean theorem has negative distances involved. No. But you can actually make a little conceptual progress by realizing that you can represent both real numbers and imaginary numbers, or complex numbers for that matter, 1 plus a real and imaginary part, as just simple 2x2 matrices. And you find that they follow all of the algebraic laws of 1, you know, the and I. And what it means in a physical sense is that time is somehow a rotated coordinate in some kind of that reality is based on a kind of subspace of coordinates. And I'll tell you right now, this is still a work in progress. I haven't figured out everything yet on this, but time is a 90-degree rotation of kind of an XY coordinate system. So you can dig deeper and try and come up with a more physical model of what time, the difference between time and spatial coordinates, by realizing that it's all based on some kind of subspace, some kind of deeper reality to space-time. Now, how do we see that like in a wave equation, which is sort of the basis for relativity? You can say relativity is derived from Maxwell's equations, which gives you the wave equation. Well, if you add a resistive term to the wave equation, so the waves are moving like through some kind of material that has losses, and that is reality. There is no such thing as a pure vacuum in outer space. You finally just get down to very low densities, but even that, the light waves moving through there are slightly damped by collisions of the plasma that makes up space. And that appears as a middle term here in this wave type equation with a coefficient, I'll just call it D. You can kind of just kind of a diffusion coefficient or a resistive coefficient. And that represents, by the way, the wave equation you could derive without any particles at all. It's just fields. But once you add the real effect of plasma electrodynamics with the collisions between plus and minus particles, protons and electrons, let's say, then you get this middle term. And this middle term, these terms, you can have time going forward or backwards, just like you can have waves that ripple out from a disturbance, or you can actually have them come down to a focus. But once you add D, it becomes an irreversible process. In other words, the waves are damped. Time must move forward as the waves drop in amplitude as they travel. So what is the physics? So that physics introduces entropy. This middle term introduces entropy with time as just a single derivative. And what it is, it's microstructure. It's subatomic particles. And they have a density. They have a cross-sectional area for collisions. And then, of course, we'll just have this same speed, c. But the product of densities and cross-sectional areas, these are all associated, these are new physics. They are associated with subatomic particles. And in fact, the subatomic particles, I believe, come into being because of a hidden fifth dimension that determines their size. So, where am I going with all of this? Time is entropy increase created by scattering of field waves. The waves themselves make bounce off of particles, like Thomson scattering of electrons, laser beams off an electron, and it disrupts instead of having a plane wave, now you have a bunch of ripples, spherical wave fronts moving away from where the particle was. And that adds your time irreversibility. So the wave equation gives you a fundamental relation between time and space. It couples time and space. But what makes time irreversible is a substructure, a sub-reality, a hidden dimension. And that is why time looks like an illusion in relativity. And that's because relativity does not require subatomic particles. Look, we always insert subatomic particles by hand because that's experimental, but that's experimental. Relativity does not predict particles. Subatomic particles, and subatomic particles, the scattering and disorder amongst them is what gives you time that is irreversible, time that is imaginary, not illusory. The time enters as with an imaginary number attached to it. And that's what makes time, as we experience it, to march on. Time marches on because it is not an illusion. The rent is due, and that may be imaginary, but you still have to pay. So, like I said, this is still kind of a conceptual work in progress. Oh, that's just some math I wanted as a backup. That basically just shows how you can take a spherical wave equation and turn it into basically a plane wave equation divided by R. So anyway, and there, of course, the two matrices. So, yes.
Oh, that is awesome timing. We were at the very bottom of the hour, so I'm happy to put up your 3i Atlas, but I didn't want.
All right, 3i Atlas, bring it on. Unless there's a question as to why I have imaginary coordinates.
Well, let's
have imaginary playmates. I have imaginary coordinates.
Let's come back to those. Let me put this up. Examination of 3i Atlas.
Absolutely.
And this is super big and super timely.
This is big. We've had a development just in the last 24 hours on this. Okay. As you know, we seem to be living in a shooting gallery, and we all knew that there are a lot of asteroids flying around the solar system, and apparently between stars themselves in the galaxy itself, there are moving bodies moving between stars. And one way we can tell when something is from an interstellar system is it comes in going really fast, much higher than the escape velocity from the solar, from the sun's gravity. So we have now apparently seen at least 3 of these things in the last roughly decade. And this one that's come in is the biggest one, and it's raising a lot of questions. I'll just put it that way. And there have been developments just in the last 24 hours. Okay, first I'll just give a context to 3i Atlas, Oumuamua, and Halley's Comet. Halley's Comet is just a comet that is bound to the sun, and it comes in and gives us a light show every 76 years, and that's normal. What has been abnormal is we've been starting to pick up these interstellar visitors coming in much faster than Halley's Comet. And so I'll discuss that, and then we'll focus on some of the extraordinary details of Oumuamua. It truly was a very alien object. And then a second really quite alien object, 3I Atlas, has now arrived. And these objects are very strange and very improbable. And then I'll summarize. Okay, we're all used to the idea of comets. Halley's Comet is one of the most famous ones, comes around every 76 years. Now, when a comet comes into approaches the sun, it develops a tail. These things are dirty snowballs. If people looked at Halley's Comet on its last visit, and they found a lot of water vapor. And it was basically sand and water vapor. So it's beach sand, basically, frozen beach sand. And what happens is it gets closer to the sun, part of this water starts evaporating and comes and raises the dust that's embedded in it, and it makes a tail. And the tail always faces away from the sun. So even though it's coming in from outer space and the tail faces away from the sun, then when it leaves, it still has a tail, and the tail is pushed out ahead of its path. It's pushed behind it when it comes into the sun, and then on the way out from the sun, it actually reverses, and the tail actually points away from the sun, so it actually is pointing in the direction of its motion. So we're used to that. We've studied a lot of comets, and but now we're discovering that unlike these other comets, there are objects that are from another star system. We can tell that because they come in really fast, much faster than the escape velocity at infinity from the sun's gravity. So the first example of this was what was called Oumuamua. It was spotted because it was really fast moving, but there were a number of other peculiar things. First of all, it was easy to explain why it was moving so fast. It was interstellar from another star system. Okay, that's fine. However, the peculiarity of it did not, or let's say the exceptionality of it did not end there. And this became a matter of concern. Its shape is very unlikely. It's shaped like a needle. It also followed an extremely unlikely trajectory for some object flying in from another star system. It's also because, for one thing, it only passed, it came into the inner solar system, but it only passed one planet closely, and that was us. It also had unlikely dynamics in that it sped up as it headed away from the sun. People have never seen a comet do that. Like Halley's Comet comes in, whips around the sun going really fast and then it starts heading out of the solar system. and it slows down because it's now fighting the sun's gravity. And there's some kind of small rocket effect due to evaporating ice. But that's much less important than the fact that the comet is slowing down due to the sun's gravity. So the problem with the Oumuamua is it did not only not slow down, it sped up by about 40 miles an hour. I mean, you could sit there with a speed gun and clock it. And I'll discuss the opinion of Avi Loeb in a moment. First, let's just talk about its shape, its trajectory, and its dynamics. They didn't get any direct images of it. All they got was what's called the light curve. And the light curve didn't look like any comet they'd ever seen. They assumed at first it was a comet. And they actually, but when they bounced radar off it, it didn't have radar like a comet. It had radar like bare metal. And not only that, it was rotating, but its rotation light curve indicated it had a 10-to-1 aspect ratio. 10-to-1. Now, we've seen pictures of, we've landed on comets. We've seen a lot of pictures of comets. We've seen a lot of pictures of asteroids. They all look like potatoes. They look like a potato. But this one looked like a cucumber. Like a long cucumber. This thing didn't look like anything anybody had ever seen before. So that was the first thing. The first peculiarity was, well, it was interstellar. Okay, makes it unusual. The second thing that made it unusual is it didn't look like anything we'd ever seen before. This thing was truly alien from outer space. Now, here's the other thing that happened. It had a very unlikely trajectory. It came in from kind of, when it was far away from the sun, of course, no one noticed it because it just, it was way far out there. It was dark. It didn't light up like a regular, it did not light up like a regular comet with a big tail and everything like that. No, it came in, whipped around the sun, went below the ecliptic, which is the plane of the orbits of the sun, and a plane of the orbit of the planets orbiting the sun, and then ended up almost parallel to the ecliptic. And it passed close to only one planet, and that was us. In fact, it came out of the sun, so nobody saw it till it had actually passed the Earth. It came out of the sun just like an old fighter plane from World War II. So nobody was watching for it. It went flying by the Earth like a bullet. It also emerged from below the ecliptic to above it once it passed the Earth. And then as it was heading out of the solar system, instead of slowing down due to the sun's gravity, it actually sped up. Now, this time they were bouncing radar off it. And the radar looked like returns from a metallic surface. They did not look like returns from any dusty dirty snowball. And it didn't make a tail. It didn't have any water vapor. So this thing looked completely strange based on our experience of objects like like comets and asteroids that we're used to. Okay, it sped up by 40 miles an hour, and it gave no water vapor emissions. People said, oh, well, it's evaporating water, and that's giving it kind of a jet effect, though a lot larger than we've seen on any object. No, there was no water vapor coming off it. There was no cometary tail of anything that could be identified. So now, Professor Avi Loeb is a really smart guy. And he says what everyone is thinking. He says, this looks like it was a reconnaissance spacecraft of the Earth. It looked like somebody flying a probe into the inner solar system to look at the Earth, and it flew by. It flew out of the sun, so nobody even noticed it until it had passed the Earth and was heading out of the solar system at high speed. And so this thing looks like it was an intelligently designed trajectory and object, and the 10-to-1 aspect ratio, that doesn't look like an artificial, that doesn't look like a potato at all. And so he said it was possibly an alien reconnaissance of Earth. Now, as anyone who knows me, I'm absolutely convinced we're not alone in the universe. And in fact, I don't even, not only are we not alone, if you want to know what the intelligent life in the rest of the universe acts like, just turn on the news, because we're typical of the intelligent life in the universe. We're not an aberration. So I tend to agree with Professor Loeb's opinion, and I'll be saying so quite loudly in the next couple months, because we're just getting into this second encounter with something that looks strange and interstellar. So my saying is, if you're not a little bit paranoid, you're not paying attention. Now, the object comes in past the orbit of Jupiter. This thing is coming in almost exactly on the plane of the ecliptic. And it's going to pass, it comes in, it does a very close pass on Mars. And then when it's leaving, it does another close encounter with Jupiter. So what I said it looks like is somebody is doing a follow-up reconnaissance of our solar system. So and here's a more detailed version. Here's the path of this object, 3I Atlas. Here it is viewed from above the ecliptic, and here it is on the ecliptic. You can see it's almost parallel to the ecliptic, and that in itself is very strange. In order to intercept two planets like it's doing, Mars and Jupiter, it has to be in the ecliptic. And so it's not going to pass near the Earth. In fact, what it's going to do, it's going to pass Mars, when the Earth is on the other side of the sun from Mars, so we can't observe it directly. Okay, we're starting to get images of it. It looks like a fuzzy ball, but it's already, even that is peculiar because it's coming in. The sun is over here. This thing has a reverse tail. It's approaching the sun. And you would expect that if it was a dirty snowball, it would be evaporating on the sun side facing the sun and forming a tail that radiation pressure would then force back out. So it would, the comet's tail would go in the direction opposite to its motion, but instead this one is doing the exact opposite. The tail is pointing toward the sun. And that means this thing is made out of something that we don't understand. And they're still arguing about they're starting to get spectra from it, but it doesn't seem to contain a lot of water vapor, unlike the dirty snowball idea. So, what are the odds? We have two very peculiar events. We have been visited now by two interstellar objects, or we're about to be visited by one, and we've already been visited by the other. And these things were really strange and improbable. What are the odds of something falling in from from another star system and making a very close pass to the Earth? The only planet in the solar system that it made a pass by was the Earth. And now we have a second one, and it's passing by Mars, which would be kind of the next most interesting planet in terms of terrestrial bodies. And then Jupiter, which is the biggest planet. And so this, I'm sorry, friends, this looks like a pattern. And I say, let's err on the side of caution and throw everything at it we can. And this is what Avi Loeb is suggesting. We have a probe out by Jupiter. It's already done its basic mission. It's called Juno. And it still has enough propellant on board that can actually get out of a orbit around, it can do basically a gravity assist off of Jupiter and run out to where this object is going to pass near Jupiter and get pictures and magnetic field measurements and all sorts of things. This is a fully capable spacecraft, and it's right there at Jupiter. All we have to do is divert it. And in the last 24 hours, Congresswoman Luna has urged that NASA continue the Juno mission, which basic mission has already been fulfilled at Jupiter, and go chase this interstellar object. And somebody would say, well, oh no, we'd rather look at Jupiter. No, do it for the science. I mean, how many chances do you get to examine a interstellar object moving like a bat out of hell with a spacecraft that's already on station? Just do it. To me, this is like just a basic intelligence test. And if I might observe, if somebody says, oh no, we can't do that, I would want to know why. Don't you want us to look at this thing closely? Because, you know, we know, and Congressman Luna especially knows, that the government has got cards regarding, let's say, the presence of intelligence in the rest of the universe. It's got cards it's not showing. So I say we divert the Juno mission and begin doing this immediately. Better safe than sorry. So here's the Trojan horse outside the gates. And the two guards on the gate are saying, one of them says to the other, I say just bring it in the gates. What's the worst that can happen? Yeah, well, that's the counsel of just ignore this thing and it will go, just ignore this probe or whatever it is and it will go away. Yes, it will. But whoever sent it will be back. If it is intelligence, if we're experiencing an intelligent reconnaissance of this solar system, I'm not the least bit curious about what the next probe will look like. I feel like we will have, let's say it's intelligently guided and planned. Remember that intelligence on Earth is found in predators. And there's nothing special about the Earth. The killer whale is the second smartest thing on Earth, and it's not called a killer whale for nothing. Another thing in nature is sharks, even the great white shark. If they see somebody swimming in the water, the first thing they do is bump them to see what their reaction is. And one of the rules of thumb is if a shark bumps you, bump it back. It knows that there are no emergency rooms in the wild. If it gets a spear, a spear gun bolt through it, this would be bad. So here's what I say. Okay. Avi Loeb is now convinced, or let's say the probability that this is an alien, that we're undergoing an alien reconnaissance has been raised by this second object, 3I Atlas, after Oumuamua. I agree with him. That's what it looks like. And we ought to react very vigorously to that, especially by diverting the Juno probe. So I would urge you to write your congressional representatives, tell them you want a diversion of the Juno probe at Jupiter to do a close look at Atlas, as Avi Loeb has suggested. So, and that's the bottom line. Better safe than sorry. All right.
John, thank you. Thank you. Let me bring everybody in. Let's give you a giant applause. Let me see. I'll bring Curtis in if he's here. Giant applause for Dr. John Brandenburg. John, thank you. Thank you. And thank you for your patience with our technical bugs.
Oh, no. This is just, hey, this is called life on the frontier. Nothing ever works quite like it's supposed to.
I could almost cry today. It's one of those weeks.
Tim, you're doing amazing. John, that was an awesome presentation. I had one observation comment regarding
yes.
I like calling it 2 Muamua. It's Oumuamua 2, right?
Oumuamua 2. Yeah, right,
yeah.
right. So, I think that's a good name for it.
Yep. So the observation was that Ray Stanford, the ufologist who spent 70 years of his life
Yes.
doing ufology, right? He just passed
I
away
met
in June.
I had the pleasure of meeting Ray.
So he made observations and collected images and did some analysis of two sizes of crafts that were similar size and aspect ratios as a Muamua, which was smaller than two Muamua, right? But
yes,
the aspect ratio of those, he said that he had motherships that were 1.4 kilometers long by 140 meters diameter, and then grandmother ships that were 14 kilometers long by 1.4 kilometers thick. So it's an interesting overlap, if nothing else, right? Who knows whether or not those were something else, but the aspect ratio and the general size is an interesting overlap to these two interstellar objects.
Yeah, they don't have an absolute a very good size estimate of this Oumuamua 2, but they think it's like 7 kilometers. That's one number I heard, but we don't know, because we don't know how much of it is dust or whatever, or smoke screen or whatever it is. It's not making water vapor.
Hey, John.
Yes.
You said that it's speeding up, like that's some horrible, impossibility. Wouldn't anything that's stealing inertia or off of the sun, wouldn't this is nothing more than a gravity?
Oh no. They Oumuamua sped up coming into the sun, whipped around the sun, past the Earth, and then sped up. It was headed away from the sun when it sped up.
But anything that's, we whip around Jupiter in order to get out to Saturn.
Right.
So, and we speed up on the way to Jupiter, and we speed up on the way after Jupiter, because we're stealing energy from Jupiter.
The calculations I saw on the speed up of Oumuamua 1, the first one, said they had no explanation for it. So they'd apparently factored all of those things. It passed close to the Earth. I mean, 1 AU is the Earth's orbital radius around the sun, and it came within like 5% of an astronomical unit. So, I would love to read a long, detailed report on everything concerning this now, and I'm going to be trying to find those.
Yeah.
But the worst thing we can do is ignore this and just assume that everything's going to be fine. This too shall pass. Oh, no.
So we're at the top of the hour again.
Yeah.
Yeah, if it's
and I don't want to detract from anybody else's time. Do we have time for one more question? Yes. Who wants to ask the last question? I'll have a question for you. Okay, go ahead.
So I was wondering, this is about your first talk, actually. So do you think, I couldn't tell how you would fall on this issue, but do you suspect time travel to the past then is impossible and always will be? Or do you subscribe to like Novikov's self-consistency or something like that?
Yeah, it's the person who spoke to this was Stephen Hawking, and he said there's chronology protection, and basically, if you look at relativity, you ought to be able to move backwards and forwards in time like it was any other coordinate, but that doesn't happen. Time goes forward. I mean, people have said, well, space travel is possible. Why shouldn't time travel be possible? I'm sorry. Yes, it is possible, but we've done a lot of space travel, but we've never done any time travel. Now, there are physical principles that allow information to come back in time, but not physical objects. Can you go back and become your own grandfather? Or would you even want to?
I would want to try just to see if it's possible. So in the movies, they're always, when you end up time traveling by accident, for example, people try to prevent a paradox. I would do the opposite. I would do my damnedest to create a paradox because I want to know what happens next. And that's why you should never send me first. Because I'll break the universe.
Well,
okay,
yeah,
Matt, here's what I want you to do. I want you to stop the assassination of the Archduke Ferdinand in Sarajevo that triggered World War I. Okay, there.
We might get a worse timeline then.
Next week, there will be. Next time we have this meeting, we'll all agree: did World War I occur or didn't it? And if it didn't occur, we'll know your experiment was successful.
Well, no, because our memories will just get updated. So.
Yeah, so that would be the problem.
But you haven't read. There's a science fiction short story. I forget who the author is, but the title is "The Einstein Gun." And in that story, somebody does exactly that. And of course, it leads to a much worse timeline. And they immediately regret it. They immediately regret it. And they're like, oh, crap. Let's put it back the way it was.
Yeah. Well, guys, if it's okay, again, we're at the top of the hour. So if it's okay, let's put our hands together one more time for Dr. John Brandenburg.
Thank you.
Thank you again, sir. Thank you again. And then if it's cool, let's go to Matthew Szydagis, and then Curtis has an update. Would that
live
work?
long and prosper, you guys? Yes.
Oh, okay. Let me do that. Then I'm going to take everybody out but Matthew. And okay, we're making up lost time. So Matthew, you did a course last year on basically warp drives and gravity control and physics. And you are doing that course again this year. Last year, I was kind of surprised. You reached out to the APEC community and a bunch of people got involved. So my condition in this one, though, was educate us a little bit and then pitch your course.
Sure. I appreciate it. So thank you for giving me this time, Tim. I really don't think I'll need a full hour, but that just depends on questions.
Roll with it, man.
So and I, at the moment, so in a few minutes, I'll project, but I don't need to right away. I'll show my syllabus and some examples, but I just wanted to say first, full disclosure that I'm teaching a paid course. So this is hashtag sponsored, hashtag ad. So extremely grateful to Tim for allowing me to basically do a commercial for my class in the middle of APEC, because I know the principles of APEC about, everything free and everything open. My course costs money because, I got to live, I got a wife and 4 kids, but also the proceeds. So it's $125 to register, but the proceeds go. So it goes primarily to me, but that means also I can continue research on these kinds of topics that I don't get any money for until things like this have started happening to me, and I'm very lucky. But also part of the proceeds, I believe it's something like 25%, it's a fraction of the total, goes to supporting the SUOPS, the Society for UAP Studies, which is a 501c3 federal nonprofit. So it's going to go into nonprofit endeavors in the topic of UAP. So not just propulsion, but also the topic of UAP and UFOs in general. So last year, I asked him if he could please advertise my class, which is online and can be taken asynchronously. Synchronous is better, though, so you can ask questions of me and the other students, of course, and interact. And last time, the number of students I had registered for the course jumped from 25 to 50. Because Tim sent an email to the APEC email list. And this year he said, well, instead of sending an email, why don't you come on and do a commercial for your class? And I'm very, very grateful for Tim to allow me to do this again. Because in this last year, that was great that I went from 25 to 50 students registered. But this year, the situation is quite dire. right? The class starts in 10 days and there are 1.5 students signed up. So if you think, well, what's a half a student? Well, one of them like already took the class and didn't even finish registering this time. So it's literally, last time I checked, which was like a few days ago, it's 1.5 students registered. And like, that's not good. As I said, I take all the money that's made from this funnels back into research, since I don't have federal funding to do crazy topics, right? Do any of us do. So it goes right back in to getting the job done on some of these crazy topics. It's not lining my pocket. I just wanted to get that out of the way immediately so people know that it's not free, and that I'm very grateful to Tim to still allowing me to advertise. So I'm going to first show you the class and the class syllabus. Oh, I should also stress, people who have taken the class already, just ask them if it was worthwhile. One of them was our own Mark Sokol. I actually don't remember if Jared took the course, but I know several APEC people did take the class. I'm Mark for sure. I remember as one of the people there. Just ask him. Just ask him if you're not sure and you don't want to pay this large amount. Look, just ask students who took the class already, so that you're not just hearing it from me, and get an unbiased opinion from people who already took it. Well, it'll still be biased because I'm friends with these people, like Mark. So what I'm going to do now is I'm going to show you the class syllabus, which you can also get for the website. I'll also project the website and all those things. But and Jared has helpfully dropped it in the chat and the StreamYard. But I'm gonna go to the website later, because I'm going to start with the syllabus. So I'm just going to want to give you a rundown of what I cover in the class. So I've got my syllabus up right here. So I'm gonna click my screen share, and we should be getting that, assuming there are no technical glitches. Could I get some confirmation? So Tim, can you confirm that you can see?
Yeah, so it is showing, let me see, Microsoft Word. It's just a screen share on top of your desktop.
So you're seeing are you seeing me highlighting these words, the physics of exotic
Yes.
propulsion? Okay, good. Excellent. You said we were having technical glitches, so I want to make absolutely sure.
Yeah, I know. Yeah, it's
very
been one of
good.
those
Excellent.
weeks.
Okay. So the title of the class is The Physics of Exotic Propulsion for Interstellar Space Travel. And as I said earlier, it's being hosted by the Society for UAP Studies, which is another organization like SCU or APEC. It's one of these many organizations in this related space. And it's going to start late summer of this year. So it's literally starting, as I said, very soon, August 13th, and it runs through October 1st. And the class will be, well, I should be careful. There's not going to be a class if I don't get like at least 10 students, or at least 5. I'm just going to cancel it. It'd be really sad. So it's going to be 2 to 5 p.m. So it's 3 hours on Wednesdays, 2 to 5 p.m. Eastern time. But just like last year, for people who can't attend, we're going to record things, and it'll be so you can attend asynchronously as well. So but I tried to pick a time that's good for Pacific, for West Coast. It's good for East Coast. It's good for Europe even. You just got to do it really, it's late at night, but not too crazy, right? It's not past midnight. Well, depending, where you are in Europe. So again, it starts August 13th, but you can register late. You can also, but of course, try to register before August 13th, but late registrations will be permitted. It's going to use Google Classroom and Google Meet. So instead of Zoom, it uses Google Meet because it's integrated with Google Classroom. So for those of you who don't know who I am, I probably should have started with that. But I'm an associate professor of physics at University of Albany. I have to say the class is not part of UAlbany. It's not part of my teaching requirements or anything. It's being done only for fun. And my university is not involved with that. So I just want to make it extremely clear because of conflict of interest, things like that. I'm doing it on my own time. So I'm doing it on Wednesday because I teach Tuesday, Thursday. So it's outside of my normal duties. Class hours has nothing to do with my university. And in fact, I have to declare this as a separate source of income for the university and yada, yada, since I'm a New York State employee. So that being said, I wanted to say, so how can I teach a course like this? Because I am a professor of physics. I am not a propulsion expert, and I do not pretend to be one. So what I do is I rely on my friends and colleagues. So like I said, I'm teaching this course second time. So first time I did this, when I first wrote my lecture slides, I relied on friends and colleagues I have who know more about relativity, quantum mechanics, things like that, than I do. because I'm an experimental physicist, not a theoretical one. I do hands-on work, which is covered in this class. But I just wanted to say that I am not claiming to be a world expert in all the topics I'm going to show in the syllabus. But what I've done is when I was first preparing the slides last year, I made sure with people who are more expert than I that my slides were reasonable. So there's no textbook because, screw textbooks, right? It's the 21st century, right? So all necessary information will be provided during class and via email, which will include attachments of, PDFs that I've scanned, using the copyright, what is it called? Fair use. So I scan things from, books by Stephen Hawking or textbooks on physics or astronomy, astrophysics, propulsion, things like that. And I will just share for free that information of people taking the class. So you only pay to take the class. You don't have to pay extra on top of that for any kind of, everything will be provided as PDFs or PowerPoints, or links to other websites, free websites. So the course description, basically the overarching thing, this is very nice actually that we rearrange things, and I'm going right after John, because in bold here, you have the question that motivates the class, which is if ET or NHI visitations are possible, how would they get here? So in this course, what I do is I briefly cover first the history of human air and space travel, and historical claims that they were impossible. Then I go into Newtonian-based propulsion, like rocketry, history of rocketry, how do rockets work, chemical rockets, and then I move on to relativity, which obviously we've not at scale capitalized on as a society yet, as humanity's not yet developed relativistic-based propulsion. So first we're going to talk about special relativity. We're going to, and this is going to be at the math level is going to be very low, because I'm just being honest with you. I'm desperate for students to fill the class, and this is what I did last year. I'm not going, if I made this a graduate physics level class, then nobody would sign up. I had a lot of math phobic people already who I begged to take the class last year. You can ask them, and they'll say, look, that they were very happy with how I did the class. There is math, but I kept it to a minimum. But I needed some math to cover relativity, of course. So I explained time dilation, length contraction, twin paradox, and how those tie in with interstellar travel. But we don't stop there. Then we go into general relativity. We talk about gravity, acceleration, how potentially you could get something like warp drive or faster than light navigation. We're going to talk about gravitational waves and inflation in cosmology, but again, at a high level. We'll talk about wormholes, again, non-mathematically, just motivate them, and talk about the big picture. Albert Einstein himself said that you got to understand the big picture before you get into math anyway. So towards the end of the class, we're going to discuss both relativistic and non-relativistic solutions to observed UAP behavior. And we're going to, one of the most important takeaways of the class will be the difference between new engineering and new physics. So that's one of the reasons I really appreciated Charles, his wonderful presentation earlier today, because he said that he thought his Exodus effect actually wasn't new physics, but was just clever engineering or exceptions within the known laws of physics. And I thought that's wonderful, because in my class, we're going to talk about the difference between old physics and new engineering, because that's also possible, and new physics. And we separate those two possibilities and show how you can have clever exceptions within the known laws of physics and what things require new physics to work, if they work at all. So after completing the course, students will know how we know relativity to be correct, but incomplete. They'll learn the formulas, again, but not at too hard of a level, for relativistic mass and energy. And as I emphasize here, qualitative perspective for non-math oriented students. We're going to talk about the side effects of interstellar travel, increase in mass during relativistic travel, Doppler shifting, and we're going to talk about potential innovative solutions to those downsides of interstellar travel. How could humanity or another race overcome those technical challenges? We'll talk about what some of the speculative solutions to those are. And what about fuel sources, propellants? We're going to talk about what some of the speculative, exotic solutions are to shielding against radiation, to fuel sources and propellants. But again, that comes after the foundation. We spend several weeks in the class First, doing foundation of just classical mechanics at a very high level, very simple level, non-mathematical. We do basic Einstein relativity before we move forward from that and saying, well, how could those things, how could they be wrong or incomplete? And in what ways could we extend our current knowledge? So another thing students after completing this course will be able to do, will be able to identify famous UAP or UFO cases or USO of high speeds and accelerations, and be able to identify potential exotic explanations as well as potential mundane explanations for what could explain those measurements. So there are no grades. This is not for a grade. Last year, the vast majority of people who took the course were CEOs of propulsion companies or retirees or UFO people or people just enthusiastic about propulsion or space travel. And most people were in the age range of 40, 50, 60. They're not taking college courses for credit. So obviously you're going to need a computer to access the internet to do the class. But other than that, you download the articles. If you miss a class, like I said, if you need to attend asynchronously, you can download things. So it's very important though for the class to function well. I say this to my actual students at University of Albany. You've got to do the reading. So you'll be completely lost, especially if you don't know relativity. I'll do my best to explain lecture, but you've also got to do the readings I assign, which are, as I said, just free PDFs of things I just Xerox myself and scan and put on the class website. So now I'm going to take you briefly through a chronological list of topics. And naturally, some topics will take longer than I expected. And in fact, I just copy-pasted last year's syllabus and I changed the date. So I'm going to tell you what topics actually took longer and which were shorter, so you know even more accurately what to expect. Because last time I taught it was the first time. Now I know a little bit more about which topics took longer and shorter. So no tests or anything like that, no written homework, just reading. So this is what the tentative schedule looks like. And I'm going to zoom in so that you can see it a little bit better. So since it's Word now, PowerPoint's a little bit easier to do, actually. So let me zoom in like 150% so you can read this more easily. So let me go 200%. There we go. So week 1, so it's an 8-week course, like I said, August 13th to October 1st. Week 1 is a brief history of human air and space travel. Then we do an intro to Einstein special relativity and time dilation. So then, and from there we go to relativistic energy and Doppler shift, fuels and shielding for relativistic propulsion, UAP case study. So I think when I taught the course last year, I moved this to the end, so I shuffled that around. And then we move on to general relativity, space-time warping, tachyons, warp drives, and wormholes. But again, not on a mathematical level, saying, oh, this is how you build it, because I want also people of diverse backgrounds, not just people who have, PhDs in STEM. I want a diverse group of students so they can understand. So this, and then there's week 8, which is kind of, I discovered was redundant and kind of tied in with week 5. So that's why I kind of moved week 5 into week 8. We talk about UAP case studies, high velocities, accelerations, and we discuss again the difference between new physics versus the potential for clever engineering. So this is a sample of some of the things you'll be reading. So you can actually pre-read before the course starts some of these things. So there's some New York Times editorials that are just for fun. We're going to talk about that claim that space travel was impossible, claim that air travel was impossible, just to kind of, set the foundation of the tone for the course, which is that the word impossible should be used with great care. We're going to talk about exoplanets. We're going to have but before we start relativity, so sort of like in between at the end of the week 1 lecture, beginning of week 2, we're also going to cover exoplanets to talk about why the extraterrestrial hypothesis is reasonable for UFOs, why it's not dumb. It does not deserve laughter and giggling, but it's actually a serious hypothesis. So that's not propulsion directly, but it justifies the idea that there could be exotic propulsion already in our skies from non-humans. So then we're going to do a very non-physicist explanation of relativity. In fact, one of the readings I'm using is from The Physics of Superheroes by James Kakalios, where he talks about the Flash and the limitation of the speed of light. And we're also going to use Michio Kaku's popular physics book, Hyperspace. That's one of the things I read in 4th or 5th grade and turned me into a scientist. That and watching Star Trek. Some of the case studies we're going to do are the Nimitz encounter, first results of the UAPX experiment that I'm on, and the Vasco experiment that's Professor Beatriz Villarreal in Sweden. So we're going to look at some of the studies that have been done on UAP and attempts, and what kind of propulsion hypotheses can we apply to them. Talk about warp speed and wormholes. And we're going to have another reading from Kaku. That's from his book, The Physics of the Impossible. Again, you're not required to buy any of those books. I'm just going to, I just scan and put PDFs on the site for free. We're also going to look at Black Holes and Time Warps by Kip Thorne. There's a chapter on wormholes in there. And then we're also going to do read a couple of chapters from I've got a typo. The University in a Nutshell. That's supposed to be the universe in a nutshell. So it's the same, that typo is left over from last year. We're going to look at, so Stephen Hawking wrote A Universe in a Nutshell, Brief History of Time, and we're going to look at some of the non-mathematical chapters in there, the ones that are relevant to the 8 topics listed there. Some of the student activities we're going to do is last time I taught the course, and it worked because I had 50 students. 25 of them would attend synchronously. So we always had lively Q&A and debates. So I would always encourage student questions. And I would also stop lecture and ask questions like to the students. And I don't just mean questions that had a correct answer. I mean open-ended questions as well. Like, for example, is there anything truly impossible versus just difficult? And we had differences of opinion on that. Went back and forth. We obviously I can't do this directly with everybody because these are people do the classroom around the world. But I suggest activities then for people to do on their own, like counting the stars at night, counting exoplanets based on statistics. We talk about when is now? What does now mean? Lack of simultaneity in relativity. Then we do some critical thinking about reverse engineering. Right, we hear all these stories. We got David Grush before Congress. Would a real reverse engineering program be successful? How and why? Would an iPad look to Archimedes, or a laptop to Michael Faraday? We'll use the classic, loose leaf paper model for wormhole and warp drives. I'll just do that, on Google Meet with people. We might also do some sorting activities in the classic light activity to explain relativity. And I didn't do this last time, but if I get my hands on a fire extinguisher or something similar, demonstrate just simple rocketry when we're doing the history of rockets. Yeah, so that is what the course looks like. And now this is where you go. I wanted so now I'm going to project. This is the website. So you go to societyforuphysics.org/the physics of exotic propulsion. And this is where you'll see you can download a copy of the syllabus that I just showed you. Nice website. There's a YouTube video about that. It's just a really cool, graphic demo about the course. Unfortunately, it says summer 2024 because, they're not going to redo their fancy, YouTube video here. So there's like a 1-minute YouTube video that just basically it's just cool graphics, right? And so you click at the bottom of the website to register. You just click there to register. And as I said at the very beginning, full disclosure, that it's not free. It's $125 US. That being said, there's a special limited time offer. So for the first 15 students who register for the class, they will get a free second class that is going to be on theory of relativity and quantum mechanics. So remember, I'm an experimentalist. So when I'm going to be talking about relativity and quantum mechanics, I'm going to be very light on the theory, very heavy on the practicalities, on the experimental results, because I am not a theoretical physicist. I am an experimentalist. I build things. I have a lab, just like Mark, just like Jarrett, just like Al, just like so many people here. I build things. Okay, I am not a theorist. I have a PhD in physics, but it was in experimental astroparticle physics. So this is a beautiful complement to the course. It starts almost right after mine ends in October. And so special limited offer, as I said, to the first 15 people who sign up is or it might be 20. Let me click it and double check. 20, I'm sorry, I apologize, 20. And so you get the second class for free, total value of $260. So this is a limited time offer, as I said, to the first few students. So let me tell you about that second class briefly. It's not my class. It's being taught by Dr. Mark Szydagis. a professor of physics at Elizabethtown College, and co-author of Einstein's Entanglement and Beyond the Dynamical Universe. So you really can't beat this deal. So this class, as you can see, starts taking place also on Wednesdays. Also, it's a little bit later in my class in the evening, so it might be harder for Europe. You could attend asynchronously. And this one starts right after my class ends, and it's also on Wednesdays. So it starts literally a week after my class. And it's a beautiful tail end to my class because let's say you are more mathematically inclined. And let's say you want to understand not just the experimental aspects of propulsion, like rockets and more exotic things, obviously, than rockets, warp drive, things like that. You really want to get down and dirty with the theoretical underpinnings, then this is a beautiful second class to take immediately after mine. And it's free if you sign up for my class. But that's not all. And like I said, okay, I sound like a salesman now, but I said at the beginning that this is going to be a sales pitch, and I apologize in advance. I said, hashtag sponsored. Like I said, Tim gave me special permission to do this today. But yeah, that's not all. There's more, which is you will also get a free membership in the Society of UAP Studies, free 1-year membership. At the first level, which is, I believe the first one here, community supporter. So there's different levels of community supporter affiliate. And then, of course, you join the board and things. But the first level is community supporter, and you get that for free. So you get a free 1-year membership in Society for UAP Studies on top of the free course if you sign up for my course. So, again, it starts August 13th. And the last thing I will throw out a pitch for is the Society for UAP Studies has also launched a flagship new research initiative, 2 of them called Aura and Upward. And I'm not going to go into them. I'm just going to show you here the website. So people can pause the video and write down super easy link, right? No random numbers in it. societyforuapstudies.org/Aura Upward. And basically what this is a really serious attempt at getting funding specifically for UAP studies, not propulsion, but propulsion can absolutely, I don't see why that couldn't be a part of it, right? Of course not. Of course that can be a part of it. And so this is an attempt to just go to investors, get some VC, and really get like some seed funding for people. As I said, the primary focus is UAP, not propulsion, but propulsion, there's no reason why that couldn't be a part of that. And you can click this link here to submit a research proposal. I'm not claiming they have money yet, but SUAPS is working damn hard. Mike Sifone, who's in charge of it, and their advisory board, they're working their butts off trying to attract funding to these exciting endeavors. And what helps with that funding? Well, like as I said, a fraction of the money that you pay in the tuition for my class doesn't go to me. It goes to efforts like this one to try to return that money to the community and to fund efforts in this space. So as I promised, I said I only needed 30 minutes. And so now I'm happy to answer any questions at all. So I'll go back to the website for my class, but I'll stop there, and please ask me anything.
Okay. And you know what? Let me bring the gang back in. They may have some questions too. Let me see. And it looks like Curtis is not here. Curtis is working on, he's got some stuff that he's juggling, and that was why he couldn't present today. So it's, yeah, one thing I should highlight, not in a negative way, but like APEC, me, none of the people, none of us are being compensated in any way. Last year, it was like pulling teeth to let you advertise that. But then I had really amazing feedback. I actually got really good feedback on your course. And so when you asked again this year, I was like, you know what? Hey, he had great feedback last year. So, if folks are interested, so, but I just want to put that out there. APEC, we like for APEC stuff, we don't charge. It's just open, all that. So.
Yeah. So I appreciate you, Tim, so much for allowing this exception of me to advertise. I appreciate that immensely. Yeah.
Yeah. You had great feedback. You had great feedback from people. So, thank you.
Does anyone have any questions for me about the class, what'll be covered, etc.?
I have one question about the, I already forgot the name of it, the place where the little bit of the money is going to help try to, do more UAP studies stuff.
Oh, the Aura /
Aura,
Upward
yeah.
Initiative. Yeah.
Do you have any examples yet on what kinds of proposals people have presented there?
I do not, because this is brand new.
Mm.
This is brand new. I do think that one of the ideas, again, I was very honest up front about this. The first ideas probably won't be propulsion related, but will probably be things like field expeditions to find UAP and see what they are. So that's probably going to be the first focus. But I do not see any reason at all why attempts at propulsion, reverse engineering type stuff. I see absolutely no reason why that wouldn't be under this scope, because in fact, when Mike told me about this Aura and Upward initiatives, the whole thing is to make sure that they're interdisciplinary and they're not just focused on one thing of UAP, like what Mark calls, looking for lights in the sky that he thinks is a waste of time, right? He said that at Huntsville, basically, it's not just focused on looking for lights in the sky. The whole point will be to be interdisciplinary.
And then one other question about the class. So you gave me a very brief run through of the slideshow from last year. I don't think I've gotten a chance to take the course and get the full breadth of it, but there was some parts there, I think towards the end of your slideshow, where you're really getting into the meat, right? You've done all the setup and you start getting into the meat at the end. Can you give anybody just a sneak peek or a little teaser tidbit on some of that good stuff towards the end where you're bringing it all together?
You mean actually pull up one of my lecture slides?
Yeah, just a slide or two.
Oh yeah, of course I should be able to do that. Yeah, I have a crazy naming scheme though, so I'm glad I'm able to share a screen and it's working, because you know how it is with technology. Tim was so I think it's working.
We're on StreamYard. So StreamYard, along with Riverside, leverages a lot of these built-in communications features that are in Google Chrome. It took me a while to figure that out, but that's why it kind of handles the same. And I think that more and more programs will be going that direction. And overall, it's great, but it is a little quirky sometimes. So
but Jared had a good suggestion. So because can you see this?
Mm-hmm.
Excellent. So okay, here's some of the good stuff, Jared. So this is where we started talking about what general relativity and how it works, and I had some cool stuff here. What gravitational distortion of light, gravitational distortion of time, general relativity in cosmology, astronomy, gravitational waves, and then how we go from Newton to Einstein. And we reviewed GR again because this was multi-week. It ended up taking more than 1 week. Gravitational lensing in depth, deeper dive on gravitational waves and their effects. First experiments and detection them with Weber bars, primordial gravitational waves, LIGO effort, how gravitational waves actually work and how they're similar but also different from normal waves. Then we went through some fun, video explanations. I think it was Brian Greene was on the Colbert Show. We talked about first observations, mergers of black holes, and then some of the first data, and then what are the consequences, how we can use, how we speculate on how we can apply that practically, how do we apply GR to propulsion, and how the discovery of gravitational waves affects the future of astronomy. Lots of Star Trek references and Star Wars as well. So I do examples from Star Trek as well as from Star Wars throughout. And then so that I conclude the first half of these are I try to pick some random but juicy slides as you requested. This is the halfway conclusion because I ended up splitting into 2 weeks. Look at GR. And then we look at warp speed, real science behind FTL travel. We cover all the people who've written on this as Rizzo, Gabriel Rizzo, Eric Davis, Gerald Cleaver, Matt Groban. We look at Alcubierre, Notario, Vandenbroek, Eric Lenz, Hal Puthoff, Travis Taylor, and again, though, at a non-mathematical level, just try to summarize with pictures what their ideas are. So we go in great depth into time dilation, length contraction, mass increase, how to get around that with warp drive. What are some known faster than light phenomena like Cherenkov radiation and why they don't count actually. And so we look at natural examples of going faster than light, like cosmic acceleration. Here's the classic, Alcubierre picture. pictures, and then we go way beyond Alcubierre because basically I just spend like 1 minute on Alcubierre, and I'm like, yeah, he was awesome, but everything he wrote is wrong. I mean, he admits that too. Even it was just the start, and then we move on to Notario and Vandenberg and all the like more contemporary people who built on Alcubierre and improved his original idea and made it better. We spent a lot of time on Eric Davis's ideas as well. What are some of the negative side effects of warp drive? Yeah, lots of time is spent on Eric Davis. I'm biased though because he's my friend. So, met him at one of the Huntsville SU conferences. Criticisms. So this is the thing: is this class is about teaching you to think critically. Not every cool new idea will be correct. On the flip side, just because it's a cool new idea doesn't mean you discount it immediately. Like a lot of, debunkers, skeptics who laugh everything off as domain of crackpots. We strike a balance in the class where we say you use critical thinking and you reject dumb ideas that are wrong. But at the same time, you do not jump to conclusions that just because an idea is new doesn't mean it's wrong. And so we try to take that balance. We talk about like practical attempts to warp space-time, metamaterials, Jack Sarfati's work. We move on to Eric Lenz, another Eric, not Eric Davis, who talks about his own solution to warp drive, and a whole bunch of other people who've written on this topic, Bobrick and Mateer. We make connections to the UAP stories. And then we talk about, does space-time warping, is it synonymous with FTL, or are these separate things? And I make the case they're actually separate. If you had space-time warping, you would use space-time warping for everything. If you had the ability to warp space-time, you would use it to go 30 miles an hour in addition to faster than light. You would just use it for any speed because it would be so convenient. We talk about, then we tie into aliens, extraterrestrials as ancient aliens. Is that a reasonable hypothesis? So again, even though the class is focused on propulsion, we do some dives into some of these very adjacent categories just for a few slides. Again, the main focus is propulsion. Even though we cover general relativity, we do some, and we do special relativity first. We do some refreshers on special relativity in the general relativity slides. And of course, warp drive is not complete without wormholes. So we dive into wormholes and, the Einstein-Rosen bridge. We talk about tachyons. Could they be useful? And then I kind of summarize it all together there. And then we do, depending on time permitting, we got a couple extra topics. Like we could cover time travel. It's not propulsion, but it's type of travel. I do have a TEDx talk on time travel, so it's another shameless plug, but it's free, right? I have over 750,000 views for my TEDx talk on time travel, but feel free to click there and watch my time travel talk. That's not the focus of this class, so that's why I put it on as like an optional extra viewing. Then we talk about how do you do, we really dive into how can you do supersonic travel without sonic booms. We talk about Lightcraft. We talk about, Ray Stanford, and we talk about Leak Marabou and all these crazy possibilities, especially towards the end of the class. We look at what existing patents there are already that could explain some of the UAP behavior, and we dive into the case studies then towards the end here. And then we tackle all the poo-poo. We try to can we debunk the debunker arguments for some of these exotic ideas? So if that doesn't get you interested in the class, I don't know what will. Because I picked, as Jared just requested, I picked one of my favorite sets of lecture slides from that class. And I'm being honest with you, though, the class doesn't start with this. This is from, you can see here, it's from week 5. I think we ended up covering that in week 6 or 7, actually. This is towards the end because you got to walk before you can run. And before we get to some of this exciting stuff, we have to review basic physics and engineering, because otherwise this is going to go over the heads of the non-STEM students who are very welcome in my class. So I'm not going to lie to you. This is not day one. Day one is like, what's a rocket, right? We start with the basics. But then by the end of the class, this is what we're doing. And I think it's pretty badass. I hope you agree. So thanks, Jared, for suggesting that. Is that everything you hoped and dreamed, Jared? Does that answer your question?
Yes, that was more than I ever could have asked for. You're showing some of the really
I
good
think
stuff.
Curtis had a question also.
Okay.
Curtis?
Yeah.
Hey there, Matthew.
Hey.
So I had a couple questions. Well, one question is, did you ever hear the talk by Eric Ryder that he came on APEC and talked about his experiment?
No, I know lots of Erics, but not him, unfortunately. Eric Davis, Eric Lenz, but so could you tell me more?
Yeah, I guess I can follow up with an email, but he actually gave a presentation here on APEC, and he's done, how would I describe it? Let's say a high energy single particle experiment that shows that at higher energies, quantum doesn't give you the right answer. So what I'd like to do is find out if, from an experimentalist point of view, if you have any, it might take some time, but his work is on free online. It's thresholdmodel.com. And again, he gave 1 or 2 presentations here, Tim. I think it's at least one time.
Well, quantum mechanics has to break down at some point because we don't have a theory of everything yet.
Right.
We don't have a quantum theory of gravity. But yeah, your question reminded me of a very important point that I forgot to make, which is the class does not get into, except towards the end of the class, doesn't get to the frontier.
Right.
Because until the very end, we touch upon a few of the crazier ideas because I have to establish a foundation first. So I just want to make that clear that the class is not 8 weeks of like, there's this person who presented APEC and another who have great ideas and done great experiments. That's not the focus. That's only touched upon towards the end.
No, understood.
Yeah.
Understood. Yeah, my question wasn't about necessarily the course.
Oh, okay.
I'm just curious if you had seen that and
no, I had not. But yeah, the thing is, yeah, I've seen.
And the reason I ask is that as you know, with experimental, there's something that could be going on that you might not. That's why we have replication. So that's one of the things Eric's been wanting is for someone to replicate. So if you have like a grad student or senior undergrad that can replicate that experiment, that would be really great, because where he's playing is like at that boundary where it seems like quantum is breaking down. So
well, I might not have the resources because, man, I'm stretched thin in so many different projects, but maybe Mark Sokol or Jared would be willing to. They've tried replicating a lot of people's studies. That they might also be able to help, or other people in the APEC community. So I'd like to try, but it'll be tough because my semester's starting in a few weeks. And
no, I understand.
Yeah, yep. But I would love to.
It might be something for a student. Actually, the experiment is relatively simple.
Okay, so, as long as I already own, because I'm this is why I have to teach classes that cost money because I'm broke. Is basically I as long as I have the necessary equipment, then I can definitely consider it. Thank you for bringing that up. Yeah.
Yeah, you might. I mean, it's oscilloscopes and things like that. So
yeah, as long as I have the right, I mean, you might think, oh, I just automatically, because I'm a university, I have all the right stuff. No, I had to buy all of that with my startup funds, which ran out years ago.
Right,
so,
right.
Yeah.
Okay. Now the other question I have is, you mentioned, the frontier, the foundations, and you probably don't know this, but I'm actually working on a paper that basically is a unified field theory, kind of completing the unified field theory that Albert Einstein started, that program. Now, the big question is, this is a different time. This is 110 years after GR, right? And back then, he, basically showed, okay, I get, Newton's law comes out of it, and here, I got the perihelion advance of Mercury. And that was enough, right? And in this day and age, the big question is, you get something and, okay, it looks like it covers pretty much all the sectors and explains inertia, which is what the main thing about this. This effort is the main physics is what is inertia, right? Why is it have the potential it does? Why does it behave the way it does? And what can we do about it, right? So the whole thing about propulsion is what can we do about inertia, right? How can we manipulate it? So the question I have is basically, do you cover, or what are your ideas in terms of, okay, let's say you had a theory like that, what would you use to check it, right? What would you, it has to replicate or give you the existing laws and some kind of limit, correspondence principle. But what other things would you look for that would give you confidence?
That's an excellent question, and I do cover that in the class towards the end a little bit, but I try not to, because I know, like you said, you're working on this, other people are, and I don't want to, pick just one or two examples. So I try to just be very broad and say, look, there are lots of very smart people working on potential extensions. And I start by giving example of the historical Kaluza-Klein theory. And I try to motivate how there have been many attempts, and there are many people working on trying to get a full theory that marries, quantum mechanics and relativity. And then I spitball some ideas on how you could test these things. I'll give you one example. It's not the best one. It's unfortunately just the first one that popped into my head, because it's 47 minutes past. I don't want to dig through my lecture slides to find the exact page number where I go over this, but I definitely do. So that's a great question. But so here's one example that just popped into my head. Is one example I mentioned in the class is that you can look at very high energy cosmic rays to test some new models, because at very, very high energies, if space-time is quantized, for example, or if there are extra spatial dimensions rolled up, as string theory, Kaluza-Klein predict, then what could happen, depending on the nature of those extra dimensions or the nature of the quantization of space-time, if it is quantized, right? I'm not sold on that idea, but it might be. And if it is, then what happens at very high energies is you get Lorentz invariance violation. And what that means in layman's terms, I'm sure you get it, I'm saying, but for everybody on the call, make sure everybody on the call, people listening on YouTube later, that means that basically very high energy particles will appear to travel faster than the speed of light in vacuum, or slower, but typically I've seen is the prediction is faster, because what basically happens, and actually I know why that popped in my head. It was subliminal because of this picture. This is a random picture from the cover slide to illustrate, gravitational. I like this better than the rubber sheet, because come on, rubber sheet, that's like old hat. We don't live in a two-dimensional world. So I like this, the grid collapsing towards mass is a much better picture. But basically imagine that space-time is quantized at like the Planck scale or something. And what could happen at very high energies is that the de Broglie wavelength, or the wavelength of the particle, becomes smaller than space-time quantization, which is not possible. Space-time quantized. So then what happens is it's like you jump from beep, beep, beep from one point to the next, because the points in between literally don't exist if space-time is quantized. So that's one possibility. And I know people have looked at this in cosmic rays, but the thing is that we haven't looked hard enough yet, because some of these crazy ideas, people poo-poo them, and we don't look at them hard enough and publish papers on them. But I do think that people have started looking at that possibility in cosmic rays. So that's the one example I can think of, is studying high energy cosmic rays to see which of these models, unified theory models, make a prediction that's testable at the very highest energies.
All right, thank you.
You're welcome. Oh, awesome. I should say cosmic rays, I'm sure you know this, or they go like way higher in energy than the best particle accelerators we could ever build. Like there's no comparison. And so that's why I said cosmic rays and I didn't say LHC, the Large Hadron Collider, because the Large Hadron Collider, compared to what nature can do, is it's a child's plaything by comparison to natural cosmic radiation.
Yep.
Thanks for your questions, Curtis.
Yeah, so we got about 10 minutes before the top of the hour. I mean, and we could go until 4 and then have Curtis go, or if Curtis wants to go now, it's whatever works for you guys.
Yeah, if there are more questions for me, I'm happy to answer them. But if not, I'm happy to. What do they say in Congress? I cede the rest of my time.
Okay. Well, yeah, Matthew, thank you again. Thank you again. Again, I had great feedback on your stuff. This is not a profit-bearing activity for APEC at all. It's just, trying to help you out, because you do great work and you're a massive community contributor. So, well, guys, why don't we go to Curtis then? Curtis, you have a lab update, and then you had mentioned being able to present today, but I added the Charlie Buhler thing in, so it's up to you. It's up to you and the guys.
No, I'm gonna need to do that after the paper's on archive. So I wasn't able to complete it this week.
Okay, so let me bring the lab update in.
Need to wait a little bit longer for Einstein's unification.
Okay, I will take everybody else back out. So I guess lab update, and then we'll go back to open discussion. Drew already did kind of an update, but happy to have him back in or whatever. So
Okay. Yeah, and at the end here, I'll talk about a little bit about the theory. So at the lab, I'll skip this. And so we had a failure at the pump support table. So this is the roughing pump that basically, I guess that the pump oil was leaking or condensing. So hydrocarbon condensate was accumulating on the table and broke down the bonds or what have you in the plastic. And the pump is pretty heavy. It's about 130 pounds or so, 125 pounds. And so it fell down. This is a picture from before. Luckily, it didn't like drag down the turbo pump. That's the more valuable of the two. Costs a bit more, and can cost substantially more, especially new. So this is where it is now. So it was rescued and put back in place. There's a temporary filter here. We got to put something else there. Anyway, so luckily that's back in place, and there was this table this table was actually something that was built by Hal for us to mount the pendulum experiment that was used to be done in air off the top of the ceiling. So we put that, we repurposed that. Our Jim had the guys at the lab techs and a guy from the local company that sold the pump. One of those guys came over and helped us out with getting this fixed and put back in place. So we still have some work to do to clean up the mess you can see down there with the wiring and all that. But luckily, everything's good. Nothing was damaged permanently from what we know now. The other thing that we made progress on is the linear experiment. So you can see here on the right, you can see the magnetic bearing is kind of on a rail, and you can see below it there's kind of a cylinder. The plan is for now is to do this in air, I believe, is what Jim has in mind, because right now we don't have a mechanism to recenter. Because if we're able to get the thing to move, when you're in vacuum, you can't just open it up and move it back. So I think the plan is for now is in that cylinder, we're going to put caps so that whatever happens with the device, if it is pumping air, that shouldn't give us a net force, right? Because we're going to cap the ends of that after putting the device in there. So we're going to do some runs like this in air initially, and we're working on a way to center it so that we can put it in the vacuum and have a centering mechanism so that if the thing goes off center, we can move it back. And of course, you can see down here there's some set screws that are used for leveling. And so once it's leveled and in the vacuum, like I said, we're gonna need we have to devise a centering mechanism. So pretty soon here, we should be able to do some experiments with this linear rail and see if we get motion. Of course, if we don't get motion in the air, it's likely that we wouldn't get it in vacuum, even though the air could be producing some counter forces. We don't expect the net force to be something that would cancel, but it could be. So anyway, so that's built. That took a while for us to get that done. And so, yeah, so it's kind of 2 steps back and 1 step forward here, but we're progressing. And, the linear experiment is very important because right now with the torsion balance, there's a lot of nonlinear dynamics, and this makes it a lot more straightforward because it's basically hanging and in that and constrained to a linear motion. And so if it is stick slip or something like that happening, we know that some of that happens with the bearings and the rods of the device. Then it's not going to the center of mass is not going to move, right? We know that from basic physics, so that doesn't happen. So again, this is a step forward. Now, just to give you an idea, the mass of that magnetic bearing there is about 1 kilogram, and the which is on the order of magnitude the same mass of the torsion balance. So the torsion balance is about 830, 850 grams, so close to a kilogram. And with the mass of the device itself, it was closer to a kilogram in total. So this is not much. It's a little bit heavier, but not much more than the torsion balance. And as you guys know, we're able to get that torsion balance moving quite nicely. So if we can do it with that, we should be able to see motion with this. So that's where we're at. Now, in terms of the theory, so I've got the outline done. The unified theory is complete. There's a lot of work to do in terms of the particle sector of the model, like how particles work and what they're made out of, and all the neat things that are in there. So it's like a whole world in itself. What's really neat is I'm getting to use all my nonlinear dynamics and chaos knowledge in this, which is really cool. So I'm excited about that. I think that this first paper is just going to scratch the surface, and there's going to be a lot more work that needs to be done. So that's what's exciting. So once I upload this to archive, I'll be able to give. Probably it will take a lot longer than an hour. So I'll talk to Tim about how we're going to do this, but I'd like to present it here. In addition, I'm referencing papers that I've been giving pre-published papers, and I'm hoping that those guys publish their paper, or at least put it in a preprint before I don't want to beat them to the punch, although they're further along than I am. So I'm hoping that they get their stuff out so I can, naturally do that. But I am going to, of course, credit them for the parts they've done. But again, this is, if you guys want to know what I've been working on, if you study Einstein's unification attempts and Mendel-Sachs unification attempts, it's along that line. So basically that's, if you guys have seen my previous talks and, seen the things the slides I put up in the, everything that we've been talking about the last over a year and a half or so, since I've been, maybe 2 years now since I've been active here, you can kind of maybe piece together like an idea of where I've gone with this theory. And again, the theory is something Jim has agreed that it's probably the right answer for inertia. So that's quite a lot. But again, I am working on trying to get the particle sector at least first order correct, because physicists nowadays, that's one of the things they look at. Are you giving us the particles that we're familiar with, right? Maybe not the standard model, but the standard model should pop out in terms of the same way that Schrodinger's equations gives you the periodic table, right? So that's kind of what is expected, and one of the things I'm working on. So that's about it, Tim.
Awesome. Well, Curtis, thank you. So I think that just about does it for lab updates too. So yeah, absolutely. Thank you. I know you've had some other stuff.
I have a question, actually. So,
sure.
Apologies, since you probably have answered this in the past, but I wasn't familiar with your work. Do you have explanations for dark matter as well as dark energy in your approach?
The first paper, I'm staying as far away from cosmology as I can,
okay.
other than the fact that the particles, their stability depends on the numbers we have for cosmology, things like the size, the volume of the universe, and the average density. Those give me the particle masses that are stable in my theory. In terms of the cosmology, there's a book that Mendel-Sachs wrote that covers cosmology to a certain extent. And but again, the thing about cosmology, the problem is that we don't have a unified theory. So the things we're talking about are based on theories that we know are incomplete. So I'd rather not say anything or make any claims. But that being said, like what we measure, I'm definitely taking that into account, right? The densities we get and all that kind of stuff.
Yeah.
And so cosmology itself, kind of like as a preview, understanding why light does what it does, right? Like in terms of redshifting, we do know that in just standard GR, right? If you take the Schwarzschild solution, most of the time in GR, Schwarzschild solution is treated as the external, like outside the mass, right? But there is an interior Schwarzschild solution, right? Now, one of the things, kind of conceptual things you can think of is like if I were at the center of let's say a neutron star, and I dug a tunnel to the surface, I shine a light to that surface, what would happen to the light? Would it stay the same, redshift, blue shift, right? That's probably a great, thought experiment. Well, if you look at the interior Schwarzschild solution, as the light travels, it does redshift, right? So now if you think about, some distant galaxy where light is headed here, and you think about that light's experience, right? That light doesn't know if there's, once it gets here, it doesn't know about the matter past it, right? It has its own light cone that it's going to see. And so there could be, in terms of like that aggregate volume, that could be redshifting the light. Now, these kind of things about GR is not taken into account in standard cosmology. So there are cosmology models where they call it Schwarzschild cosmology, and in the news there's been these talks about, oh, we're in a black hole, but that's not really. So basically what that means is like, okay, the Schwarzschild cosmology might be part of it. So
yeah,
cosmology, the universe is very complex. Like there could be a lot going on, and without a full theory, for me, it's like hard to say, okay, is it this, that, or the other? What we measure, I think I would take dark matter and dark energy as statements that we don't know why this effect is there, right? That's fundamentally what it is. It's like an experiment saying that it looks like it's extra matter, but we don't have it with our current theories. We don't have an explanation, and that's how I would treat it at this point until we get a full theory or a self-consistent theory that we can test and say, okay, what it is. Have some ideas, and I do have some ideas, but again, I would rather establish the theory first and then apply it to something as complex as cosmology. If that makes sense.
Yeah, it does. Yeah.
well, yeah. Well, guys, let's go to open discussion, and we'll just kind of open things up. If it's okay, I will be super quick. I want to share. I do want to share a couple things with you that I've been working on, and then I will slide again.
Sure. Tim, did Jared have a question? I don't know if he raised his hand before we.
Oh no, I was gonna say I also have a brief update on another UFO sample, but I'll let Tim go.
Yeah.
Okay.
Thank you.
And Curtis, if you could mute yourself because you got some background noise.
Oh, that was Matthew. There are chillins. Chillins floating around.
Okay.
I'm sorry, I muted. I'm sorry about that.
No problem.
Okay. Let me see. So I will. Let me see. I will do. Yeah. Okay. So that's not good. Let me share. Okay, and that's. And now it's not going to stop sharing. Hold on. Okay, I'm going to have to do it like this. Okay, so on my YouTube channel this week, very quickly to run through it, not all of these are stuff that APEC folks would be interested in. I did post a full hour with Charlie Buhler. We had some Q&A at the end of it. That's the first on the channel there. So that is there. Another one that you guys everyone seems to be interested in this, Avi Loeb. I did a podcast with him on 3i Atlas, and one that is actually worth paying attention to is George Hathaway talked about gravity control experiments. So that is, he went in depth. He went through a bunch of projects. We're going to do something on energy in the near future as well. And speaking of energy, I also did a podcast with Harold Sonny White, who claims that he's harvesting 0 point energy from the Casimir effect. And the one reason I wanted to mention that was, in addition to that, there's another one. This is not my interview. This is Jeffrey Mishlub's channel, New Thinking Aloud. Tom Vallone sent this to me. Tom, I cannot stress how excited Tom is. So this is Garrett Modell's work. Tom was quite literally jumping up and down saying, you have to talk to Garrett. You have to talk to Garrett. Garrett Modell is waiting to do more media before he publishes a paper. At least that was what he'd said to me. But I did want to point this one out to you guys. It's called Can We Harvest Zero-Point Energy with Garrett Modell? Okay. And so, sorry. So this is, here it is. Can we harness zero-point energy with Garrett Modell? So there's that. So I will stop sharing now. I also have a couple of videos from Isaiah. I'm not sure if it's cool to share those or not, but that's probably won't hurt anything, but I can wait as well. So.
And you're going to be going down to Isaiah soon, and you're going to get a whole bunch more video.
Yes, I will get more videos. So I'll wait to share those. The thing that caught me most off guard was Sonny White's thing about harnessing zero-point energy. And if I understand correctly, he's putting an antenna basically inside of a Casimir cavity. Garrett Modell is taking kind of a different approach to it, but they both claim to be generating real usable amounts of power. Small, tiny power, but still real amounts. So that's all I got. That's Tim. Yeah, and yeah, again, open discussion, guys. So I would say go for it.
Okay, an antenna has to be made of something. Most likely metal. Even if you're down at the Casimir spacings, wouldn't the let's say you have a little metal wall, X number of atoms high, X number of atoms long, another little metal wall, the separation is the Casimir effect gap. If you put an antenna in there, doesn't it split the distance between any of the walls? So
I think it would where the antenna is. So it's almost like a bucket. The antenna is kind of closer to the bottom of the bucket. So you still have a resonance area there above it. So
that's cool.
Yeah. The other thing that really interested me about it was he's using chip fab techniques to create these. He actually showed me a couple of transistor boards, basically, chip fabrication, right? And I am not sure if this was from him or Garrett in that video that I showed you guys, but somebody had said the efficiency is comparable to solar cells. And that's really low, right? That's low efficiency. But if you can put these things on a transistor and put thousands or millions of them together, you might be able to generate, again, usable amounts of energy for stuff like microelectronics. And that's zero-point energy. That's the part that's mind-blowing, for me at least. So.
Jared?
Can I share my UFO sample update now?
Yeah, right, share your UFO sample.
Right after we hear about the gravel flyer update.
Always gotta poke that bear.
The debrief is going to be running an article that may not be positive about that as well. Just so you guys know.
Don't know when they will, but so we got another sample coming our way. This is probably the most mass of UFO samples, purported UFO samples that I have seen to date. The last one that I saw was a really big sample, but it was just one of those. This is a 5-gallon bucket full of samples from UFO landing sites over in Israel over the last many, many decades. So this one that the person is holding over here is interesting. It's the one on top of the bucket there. It's interesting because one side of it is very smooth and curved. The underside of it is pretty rough. So that right there, right off the bat, is unique. That shows potential manufacturing of some kind, that it's, smooth and has an even curvature on it. But the really interesting part is what happens when you look at, here we go, I'll go down here first. When you look at some of the analysis that's already been done on these samples, right here, they took two different sites. I think it was XRF or EDS. I'm not sure how exactly they got the data, but it looks very XRF-y. Anyways, they took these two measurements and they came up with these averages of what's over those two spots and all the elements that are in there. And for most folks that aren't, familiar with the periodic table, this group of elements is extremely crazy unique because it's an entire row of the periodic table. It's the lanthanides. So if I scroll up here, so element number, the big half here, that's 54%, that's indium, which is a metal somewhat similar in some ways to bismuth. And then the rest of these over here, most of the rest of these, except for silicon and oxygen, are elements 57 to 70. And the only one missing there is element 61, which is like an artificial, human-made element. You don't find it naturally in nature. But the rest of them, it's all these lanthanides. And the ratios of them is all pretty daggum similar, between 4.5 to 6.5%, right? That's really weird. So what it looks like that sample is an indium lanthanide, which normally when you see those kinds of things, I've been going through the papers and the research on this stuff, trying to find, is there anything else out there in the world like this that people make for any reason? And the closest that I can find is that indium lanthanides have a few very specific use cases. They can be used in some glasses and ceramics, but they're also used in some magnetic applications because some of these elements over here have some of the crazy strongest magnetic moments in them, as well as some very interesting electropermittivity things. So the fact that you got all that bucket of rocks that is left, this is not from a single landing site, right? Like a few of these would be left over at a landing site, and then, fast forward a couple of years and there's another landing site with the blackened charge circle there, right? And maybe some Israeli, cops or something saw it land and take off, and this is what was left behind, right? So they've been collecting these over years. But for some reason, the story goes, the aliens keep leaving this stuff there for some reason. Well, we know that the Ubatuba stuff, it seems like slag. Maury Island, it seems like slag. Like, you get rid of slag because you don't want it anymore. Maybe they're trying to maintain a very special balance of these elements here. And once the balance gets thrown off too much, it doesn't do the thing. And so they melt it and get rid of it. But the fact that we have one of these samples has this smoothed, curved surface here, I don't know. That's kind of an interesting feature that might suggest it's not necessarily slag. Additionally, I've been going through like every single one of these elements, every combination of these elements, what happens when you use these elements in any permutations together, right? And this is beyond preliminary, right? This is near wild guess, just to preface. But it looks like these elements, because they're so useful for magnetic type stuff, it looks like they're all balancing each other out with the end goal of dealing with plasmonics. So if anyone recalls from the arts part stuff that I presented, my takeaway from the arts parts is that is a terahertz modifier, right? So it's potentially you hit it with some form of terahertz, and then it modulates that and creates a circular polarization on that terahertz that then goes out, right? And so you got a spinning terahertz beam coming out of arts parts for whatever reason. Well, Linda Moulton Howe said that when she was at one of her presentations on arts parts, that this Area 51 S4 guy came up to her, proved his credentials, and then told her, yeah, that's like the outer layer of the craft. The inner layer is actually like almost pure indium doped with some other stuff. Or not indium, pure iridium is what she heard. So now I'm kind of really stretching. Maybe she heard iridium, but maybe it was actually indium. And maybe pure is relative. Maybe it's not 99%. Maybe it's 54% indium with all these other things. What if, spitballing here, what if arts parts and these kind of things are two halves of the same mechanism, right? Because when you hit this particular stuff with terahertz, according to the theory, when you hit this stuff with terahertz, it's going to hold on to these magnetic fields, because when you twist light, it can create really strong magnetic fields, but they're super temporary. They're ultra short-lived. Well, this thing looks like it might be able to capture those and make them live longer and magnify them and direct them. So for whatever reason, maybe, big maybe, these samples here, they might be related to arts parts. Alternatively, it might be a big old giant psyop, and this is actually like some super secret program, once again, that, you know, they were testing something and they threw everything in the kitchen sink, right, to melt them all together. Really hard to say yet, but the biggest of the big takeaway here is you have a bucket full of samples that have fairly even distribution of the entire lanthanide group combined with indium. So this was manufactured, 100% sure. This was manufactured. The question is why?
Jared, is that material magnetorestrictive? Or does it have magnetorestrictive properties?
I'm glad you asked that. So one of the angles that I started going down into was this stuff called photomagnetism. So for those who aren't aware, photomagnetism is the idea that you have like a lattice of a metal or some kind, right? Well, you can hit that lattice with a certain frequency of light, and thanks to light matter interactions, plasmons, you can very temporarily shift the bonds between those things. Well, if that metallic lattice happens to be magnetic, you can reorient the grains very, very briefly, right? And so you can change the magnetic properties of materials using specific wavelengths of light in such a way that it might just be that this stuff is magnetoresistive in some ways, and then it gets hit with a different modulation, and it goes from being magnetorestrictive to being magneto... I don't know. There's a whole like triple Venn diagram of all the ferro and magneto resistive electric stuff. I can't remember all of it, but
okay, thank you.
You're muted. You're muted.
Sorry, that's because of the kids. Because Tim, may I tie in to what you just said and give a brief update of my own? Because for those who don't know, I did a neutron activation analysis of the art part and also X-ray fluorescence analysis, and two different neutron activations actually, and two X-ray fluorescence, like very, very carefully determining what's in there. And I gave an update in June at the SCU conference in Huntsville, Alabama, and I also spoke here on March 15th at APEC. And so the update I have is that so I wanted to first list what the top there are top 8 elements that, based on my neutron activation analysis, which isn't complete, but this is beyond, this is definitely a notch above preliminary, because I have rerun my software and my analysis code of the neutron activation data over and over and over and over again. And there's no way these are false positives. These are the top 8 elements that I detect above threshold. And they are bismuth, carbon, argon, iron, sodium, silicon, manganese, and lanthanum. That's very important because that ties in with the Israeli sample. Now, here's what's very intriguing. So the lanthanum is one of these elements where, so I was gaslighting myself. I'm like, there's no lanthanum in this sample. This can't be right. It's not in the XRF. It's not in the other techniques. It's not in the official Aero report from ORNL. It's not in the TTSA report from Hal Puthoff. I'm like, there's no way I found something that they missed. But I just can't get rid of, there's a very strong signal from not just one, but 2 different isotopes of lanthanum. And it's in there. It's in the data. So I'm sure there's lanthanum, and for some reason it's been missed from all existing analysis. So I see 2 separate half-lives of lanthanum in the data. But moreover, one of my undergraduate students, Casey, he actually sees lanthanum decaying into barium in the energy data. So we've confirmed it with time and energy. There is lanthanum in the art part. And again, why is that so interesting? It matches the Israeli sample, and it matches the And it also matches, and also it's got these important magnetic properties. We use it in smartphones, right? We're always worrying about tariffs in China and like basically the presence of lanthanum completely disproves the the art part is just a piece of uninteresting slag. What? That lanthanum is a rare earth. You only put it in if you're building an iPhone or an Android or something else that requires some magnetic properties. The other interesting thing is, notice I mentioned silicon, one of the strongest signals, conveniently omitted from the Oak Ridge report. No mention of silicon. And what is the Israeli sample primarily made of? Silicon. Okay, very interesting. You'll notice that in my list of 8. I didn't list zinc or magnesium. That's because I'm talking about my top 8 dopants or impurities or purposeful. We all know it's mostly magnesium and zinc. There's no need to mention them anymore. We're interested in is what's the secret sauce that's put in on purpose at a very, very small level, like what's the salt and the pepper. And those elements over and over again. I have no doubt they're in there, including lanthanum. And the silicon is an interesting connection. We have to be careful about, so I mentioned carbon and sodium, and those can be red herrings because it was touched without gloves for decades, right? Did Art Bell and Linda Moulton Howell whip out their latex gloves whenever they? No, of course not. And so basically we have to be very cautious to interpret carbon or sodium are probably human sweat, right? And just organics. But yeah, the carbon signal is it's like huge, but that's because the damn thing was touched and it burned and the atmosphere potentially crashed. So carbonization. So those are not to be interpreted as necessarily important. But I also wanted to share one more very cool finding that I want to share. It's preliminary and premature, but I'm very, very, very excited about it, and so is Jared. But I got another UFO sample. I don't want to talk about all the details yet here because I want to get permission from the owner of the sample. I want to be respectful. I believe in openness of everything, but also I respect people's privacy. But I do have a second sample that I got from a crash somewhere else, allegedly. Okay, it has nothing to do with the U.S. or Roswell. It's from another country. Looks nothing like the art part. In fact, I thought it was meteoric. It's just a black ball. I'm like, oh, it's going to be a meteor sample, which is cool. It could have been. I tested it with XRF. I tested it with NAA. And it has the same damn elements as the art part. Not the Israeli part, but the art part. Except the important ones. It does not have magnesium. It does not have zinc. And it doesn't even have bismuth. It has the dregs only. And I'm like, what the hell? And so it's like the art part as a black ball minus the major elements. So riddle me that, right? What the hell does that mean? And so that's why Jared suggested, what if, craft have to offload their slag or whatever, the extra stuff. But this blew my mind. I only got this result last week. This is hot off the presses. But it blew my mind. How the hell is this sample from a different decade, different providence, different chain of custody, different country, completely different physical appearance? Nothing like the art part. It didn't look like it's structured. It looked like trash, like industrial trash or meteoric. And it has the same elements, even the ones that seem to have no purpose or importance. It has all the same elements except the 3 major ones. What does that mean? I don't know, but it's pretty awesome. And we're going to publish that hopefully in a few months, and make a big storm about these discoveries.
One thing to add to that, and the sample that you just talked about, it's like arts parts as a black ball. Also, if anyone looks at the Dal-Nagorsk stuff, the Dal-Nagorsk images that I've shared before, there's images there where there's black balls that were left over. And we already know that the Dal-Nagorsk stuff also seems to have a lot of overlap with arts parts. And so now we have 2 other samples. This makes sample number 3, where you're saying the same thing. We also have this Israeli sample that has all these lanthanides. There's also yet another sample from Ireland or Dublin or something, like back in the early 80s, which was like 94% lanthanum, right? I think that if anybody wanted to look into UFO reverse engineering stuff, a really good place to start might be looking at lanthanides, because there's strong magnetic fields associated to UFOs. There's all these lanthanides present in all these different UFO samples. What's going on with that row of elements? Well, I will say part of the reason, from what I've seen, so you got the 4th orbital to the 5th orbital transition, and they're transitionary, right? So it is because of that transition where you can bump up the electrons from already really high orbital to even higher 5th orbital, right? Which that's the whole magnetic component there, as far as I understand it. So because they're transitionary there, that's what makes it so useful for the photomagnetic effect, is that light takes those 4 orbitals and puts them into the 5th very temporarily before they come back down. But yeah, massive stuff. Hit me, Curtis.
So I'm just curious. There was a mention of Avi Loeb, and I had heard that he had went to somewhere in the ocean and dug up some samples from an explosion. I'm just curious if what that analysis. Do you guys know what that analysis showed?
I offered to help him with it. He declined. I said, I can do neutron activation analysis, and I could show whether it's terrestrial or extraterrestrial, and he politely declined. I'm not important enough to be associated with Harvard. So I know he did his own analysis, but I don't recall. I don't think he did neutron activation, which is the best you can do non-destructively.
His samples looked kind of like little amber slivers, right? Little amber balls, right? Which, I don't know, doesn't look like anything else that we've tested. One other person, though, with UFO samples, it's worth mentioning, a fellow APEC member, Richard Bandurek, went on, a while back and was telling us about how he had tested some UFO samples way back when. And just this last week, like, that story finally hit mainstream outlets all over the place, or all outlets. Everybody was talking about Bandurek stuff. So if Richard wants to come back on and let people know, any more information about that, we would love to have you back on, because there's a lot of interest going on with that right now for some reason.
Hey, Jared, I'm gonna spend 30 seconds down your rabbit hole. I picked up a sputtering target of yttrium a couple of months ago, because the only reason I got it is because it's the only non-radioactive material that has a super high work function, which means that you can pump energy into this thing and it gives off electrons. It easily boils electrons off the surface. So contact me later and we'll talk about a pattern to use that stuff. That's real tricky because it's super oxidizes, which means I got to operate in an inert environment the whole time. Before I pull vacuum, I gotta have gas on that. So before I go through the hassle of putting that stuff in my sputter chamber, I want to know that I'm going to head for something, because even after I manufacture it, I got to cover that with something, because it'll corrode before I get a chance to get it out of the chamber, get it into the processing unit, and get it into the chamber again as a thruster. But you're talking about lanthanums. Those things have real high energy levels, whatever. It's real easy for them to throw their electrons off, which makes them real interesting to my end of the universe, because that's what I'm trying to do, is impart electrons as ions, basically, into my what do they call it, the plastic that doesn't let electricity pass through it. I swear I can never remember that word. Anyhow, just interesting that one of the things that you're finding in this alien slag is something that our team decided that it was worth the ridiculous amount of money that target cost to take a look at. We should talk about that some more.
Drew, can I also, I want to put in a plug for 2D materials. That's on my list.
who?
2D materials. And I don't have any guarantees there, but like, again, Michael Perrone got me into this a while back. He was talking about boraphene, right? Which is like a next generation graphene, except it uses boron atoms. And so I started doing research, and I found they have made stuff like graphene using tin, bismuth, germanium, if I remember right, and a couple of others. And when I started reading these papers, what struck me about it was the scientists basically, they did initial synthesis of this, and a couple of them were like, here's bismuthine. It looks really cool. We bet it has some interesting properties. The end. Like, they haven't even gotten into experimenting with it yet. But for the kind of stuff you're working with, right? Because you're working with thin film plates and stuff like that, there's this part of me that's like, I wonder how that could potentially be used, you know?
Yeah, me too. I would love to be doing this stuff every day. You know, there's bills to pay and places to be.
There also is an argument to be made. So Dr. Szydagis was saying how, there's a lot of carbon in these samples and people have touched them. It's also possible that while some of that carbon is coming from people, you can do a lot of stuff with carbon. Graphene comes in carbon. Carbon nanotubes are carbon, right? And there's some high technologies that use carbon. And you can use it as a binding agent. There's all sorts of different other possible use cases that could be going on in these samples. Just because there's carbon, it doesn't mean it's amazing. It doesn't mean that it's nothing. It's, it means that you should probably keep looking. You should find the skin cells or you should find the nanotubes.
The point is it's a mixture. The carbon, I'm sure, is unfortunately all of the above. It's both interesting and integral to the part, and it's also from organic human beings touching it repeatedly. I did float this crazy idea, though, to Jared that heck, could be carbon off, alien fingers or something, but that's going to be really, really tough to tell. I was thinking of a way to sort of use the carbon and try to do carbon dating, but I'm not an expert in that whatsoever. And it's messed up by the neutron activation, so I have to reverse engineer with the original date. But so I don't want to give any false hopes, but I'm going to try maybe to see if I can look at the ratios. I definitely can't detect. I'm not going to detect carbon-14 directly because its half-life is 5,730 years. But I should be able to detect products by making carbon-15 from 14 from the neutron activation, and then try to work the math backwards to try to estimate the original amount of carbon-14. I'll try that, but it's going to be very hard to conclude anything conclusive from that because the result will probably be garbled, even if it's accurate. It might be precise but not accurate, if that makes sense, because it just might be a mixture of carbon from Earth, from other sources, and it's going to be a hot mess. But I'm going to try because, in fact, it's entirely plausible. Carbon might be literally the only atom capable of life in the universe. I've heard this argument made. I'm not saying I believe it immediately, but I've heard the case made that silicon and no other atom is as good, and that any life anywhere is going to be carbon plus blah, 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 blah in different combinations. If that's the case, that would be really, really exciting to get one's hands on carbon from outside of our solar system and look at the ratios of the stable isotopes, like 12 to 13.
I got to tell you, we were messing around with carbon in the form of pentazine, and it's amazing what happens when you throw a little carbon in the form of pentazine on a thruster. It's stunning the amount of thrust that you can pack up. It's like when we were doing that, we were messing with the ones that basically store up energy and never turn off. Those were the no-off units, and we were tenfold increased. Remember when I was talking about the little dots a long time ago? Those little dots were pentazine. And the thing is about the borazines, and the carbon nanotubes and the carbon graphenes. They're all superconductors, basically. They're all really good. I mean, they may not be superconductors, but they're really, really good at conducting electricity. And our world is 100% electrostatic, so super good conducting things ain't what we're looking for. We're looking for things that are terrible conductors, but are great storers of charge, so that we can make little tiny islands of electrostatic magic. So we have a real delicate balance between storing up charge and not having it flow to the next island over, but you got to get it in there somehow. And we spent a lot of time messing around with chemistry, and unfortunately, we have a battery genius on our team. So it's you'd be amazed what those battery geniuses can come up with.
Well, and who knows? Maybe you guys can invent the successor to the lithium-ion battery too. You know, maybe that'll come out of it. That wouldn't be bad.
Maybe.
I
Do
prefer
away with the need for them entirely and just, extract the energy straight out of subspace.
My preference is miniature nuclear reactors to replace diesel generators. That's my goal.
I'm kind of one level up. One of the things that's on kind of my long-term wish list is EVTOLs, and that's coming, right? But they're struggling. I mean, they have them today, but they're struggling with power to weight ratio. If you use a gasoline engine for an EVTOL, you can use like a gas-powered generator. You have low power to weight ratio, or just high weight ratio and low charge time if you're using batteries. But I'm really excited about the advent of those.
So, Tim, are you a fan of Back to the Future?
Yeah,
Oh, yeah.
who isn't a fan of Back to the Future?
I'm still waiting for my flying car. It's 10 years late now, 2025. I still want my damn flying car.
I think that there's a bigger. If you let me, if I can proselytize for a moment. So EVTOLs, what pisses me off is when I go out and do research on this. One of the first ones that I saw was this Chinese EHang, and that's totally outdated now. That's like 7 or 8 years ago they came out with that. And it was, I believe, a single passenger or a 2-passenger. It had a half an hour flight time. It was just enough to get you across Beijing, right, where they were testing it. But that's all you need, because let me back up a sec. In the United States, they decided, hey, we need to commercialize this. We'll make air taxis. We'll have several people on board, and yada yada yada. And so these EVTOLs become bigger, and they're trying to make them more like aircraft as opposed to being like a puddle hopper, from one to the next. And that's the part that pisses me off, because what I see, and I'm sure you guys, like, if you stop to think about it, think about how much time you spend in traffic, and traffic always gets worse. And I've read studies saying that no matter how many roads you build or how much you expand roads, basically it gets worse and worse and worse. There's a maximum limit to traffic density, right? And this is the bane of modern civilization. I mean, our entire system is built around hub and spoke, and you'll always have that for stuff like tractor trailers, but for commuter vehicles, the only way to break out of that hub and spoke is point-to-point air travel, and that's EVTOLs. And so, like, once you start to go down that rabbit hole, like, what changes? And this would apply to any, like, anti-gravity or anything along those lines. If you can break out of that hub and spoke model, all of a sudden you don't have to buy a super expensive house in the middle of town around crappy neighbors. You can buy something that's farther out, costs less, and has privacy, and take, like, your plane out there, right? And so it starts to break down a lot of these density failures of modern civilization, So, like, the idea itself it's a lot bigger than it first appears. So
People don't believe me when I say this. I've said this on so many podcasts. I would take flying cars over the internet. I would take a parallel universe where there's no internet. We can't do Google, like the StreamYard we have now, but we have flying cars. People are shocked when I say that. They're like, but the whole knowledge of the planet at your fingertips in your phone. And I'm like, yeah, instead what I would do is I would take my flying car and fly to the effing library in my flying car. How awesome would that be, right? So right now I would go visit Tim. I'd be like, I'll go visit Tim in my flying car, or Jared. Like, I love these. Like, I would seriously, people don't believe me. I would take flying cars over the internet, or jetpacks. I would take jetpacks over the internet.
People get stuck in paradigms. They get.
I know. People say, "Oh, internet is so important." I'm like, I would take my jetpack and fly to the library. Right? Problem solved. I don't need the freaking internet. I can go to the library in my jetpack. It'd be so
okay.
awesome.
So the paradigm. This paradigm. This got me earlier in the week. This isn't gravity related, but so I've been watching these videos with some of the tech titans talking about various things. This one, I saw one with Peter Diamandis and Eric Schmidt. Another one was a speaking engagement with a former colleague of his. I don't remember which one it was in, and so. At the beginning of this show, Eric Schmidt talks about, the former ex-Google CEO, right? He's worth, I don't remember what it is, but it's like pushing 100 billion or something. He has enough money to do whatever he wants in life. So at the beginning of this show, he mentions he bought a rocket company because he wants to develop subject matter expertise in it, And the guy with him was like, as one does, right? He's joking because most of us don't have that kind of money, Hey, that's cool. You're rich. That's fine. So what got me was later in this show, then this fellow asked him another question, and he said, well, I'm getting to be that age where a lot of my friends are dying of really horrible diseases. I want to cure those, And I'm like, okay, so he's a philanthropist. He puts money into, I looked it up. He puts money into like environmental and, all sorts of stuff. And I'm like, it's worth more to you to buy a rocket company to learn something where you don't even have a plan to go into space than it is to like work on aging research, which is something that affects every single person on the planet. But the reason that very few people do that is because aging is such a paradigm. They're just like, oh yeah, people get old and then we die. There's nothing we can do about it.
We used to think that way about air travel.
Mm-hmm.
We will never fly. Only birds fly, and that's when they're going to fly. And we needed visionary people. Leonardo da Vinci, the Wright brothers, right? That's damn, I can't help it. Shameless plug, but I covered Da Vinci in my class and the Wright brothers. But yeah, it drives me nuts when people say X is impossible. Oh God, nothing gets me angrier when I hear people uninformed on a topic claim that something is impossible and they have no idea what they're talking about.
And then electric cars are a perfect example of that. I mean, I have a Tesla, and for me, there was a change curve that happened, right? I had a Ford Explorer before that. Gas in my area hit $6 a gallon. And I was like, this is just too painful. And so I went out and got the Tesla. And at first I was super excited. I got an electric car, all that exciting stuff. Then you get used to it. And it's like, yeah, it's an electric car. It's a car where I don't have to put gas in it. I just plug it in when I get home, And like, so at first you have this big change where like everything is so different, and then you normalize to it, right? We would do the same thing with like aging is one example, or EVTOLs. Right now, this idea of like, I would love this. Like if you could just go out into your driveway, get in your car and fly to the grocery store. I mean, wouldn't that make it so exciting? That would make it worth it to just go buy like lettuce, but then like, once you normalize to that, people will be complaining. They're like, oh, honey, I don't want to go to the grocery store. I just got home from work. Get in your EVTOL and you fly there right now.
Damn it, Tim, I want to live long enough. I want to live long enough to get to the point where it's like, I've got to go to the moon again. I just got back from Mars, honey. What the hell? Like that's the world I want to live in. And that's the world I dreamed of as a child. And I hope I get to live to see it, because I hope that by the time I'm old, they will have cured old age. I hope so. Tying into your other point. Yeah.
I think so.
Yeah.
It's like Mark flew to the beach and
Yeah, I'm actually at the Jersey Shore. So this is where the UFOs or the drones were coming out of. And I heard reports recently that there was some new sightings. So I came down here to the shore of New Jersey, and I'm all set up with the UFO detecting camper. We're right around sunset, and we'll be looking for some drone action tonight.
Keep your eyes open for Jimmy Hoffa's body too. It's out there somewhere.
Whose body?
Jimmy
Hoffa.
Jimmy Hoffa. Okay.
I'm just kidding. I'm kidding. He's in a
too,
bridge. He's in the middle of a bridge.
Yeah.
They dropped him into concrete.
It's a little busy right now, but people are going to start heading out as soon as it gets dark. Yeah, Matthew actually got the privilege of sleeping inside the UFO detection van.
That's true. That's true. Or yeah, I did, and I also got the privilege of getting kicked out by the by the water.
Yeah, but that was right in time.
Are you guys? So Tim, Jared, Drew, Curtis, are you guys Ghostbusters fans? Please tell me you're Ghostbusters fans.
Yeah.
No Ghostbusters. So Ghostbusters 2, that really happened to me and Mark. Hey, what you doing here? What's the story? Oh, hey, well, we're working here. It's the scene where the cops come and try to bust them where they're drilling. Yeah, that actually happened to me and Mark. It's officials came to hey, what you doing here? What's the story? And they had hard hats and everything. They're like, hey, what's the story here? What you guys up to? And I was like, oh shit.
Yeah, because it's New Jersey. They'll hassle you for anything.
That was in Connecticut. It wasn't in New Jersey.
Oh.
Little did they know that Mark is very anti-authoritarian. So that did not sit well with Mark.
I don't think they really cared. But yeah, what was interesting there is we lost the drone. The battery went from 65% down to nothing, and it fell out of the sky. And I just saw another report of a video somebody caught of a UFO. And as they're catching this sighting in short range, their battery dropped, and you could hear them saying, "Oh wow, our battery was just at 70%." And then the video cuts out, and in the description they said the same thing happened to them. And the people in charge of the reservoir said the same thing happened to them with their drone, and their drone was a $10,000 drone. They actually sent in a dive team to go look for it. They couldn't find it.
Mark, if you're going to want to do this seriously, you're going to need to use drones that, like is being used in Ukraine right now, that have the fiber line. So
it doesn't matter if the battery is the problem.
Well, okay.
The battery is what dies. It's not the signal might cut out too. But even if the signal comes out, the drone will fly back to base. The problem is the battery just shits out for some reason.
No, it's classic, right? It's like Close Encounters of the Third Kind, right? Richard Dreyfuss's truck. You gotta cue the theremin music, right, or whatever's appropriate for weirdness.
So you're saying you get a signal that tells you the battery is dead, and then the drone.
That's what happens. Yeah. So this happened once. We sent the data because it's actually saved on the headset. This is an FPV drone. I sent it over to the DJI, and they looked at it. They couldn't believe what they saw. They asked me for all of the footage of this drone, all of the metadata, and I sent them over. It was over a gigabyte of data, and they ended up sending me a drone for free. I didn't even have to use one of my flyaway warranty options, which would have cost money. They ended up sending me a replacement drone and battery for free, saying that this was of unknown cause, what happened with this in this particular case. So, yeah, it's definitely anomalous. Would I say that it's evidence of UFO interference. Not necessarily, we didn't see any UFOs or any spheres there, but something strange did happen, which was interesting.
I have to go, unfortunately, because I'm like really late for dinner with my family, and my in-laws are coming. Actually, they're driving all the way from Chicago, and I need to go because I'm already in trouble for. I'm going to be in the doghouse because my wife's going to be like, "You just sat on Zoom," or I'll say it wasn't Zoom, it was StreamYard, whatever. I sat on this all day instead of helping with the house. Yeah, so I got to run. All right, but this has been fun. It was great, and I loved listening to everyone's talks earlier.
Yeah, well, thank you,
Yeah.
Matthew.
All right, thank you.
And again, I should probably apologize to everyone 5 times over for technical bugs up the wazoo today.
No, it was fine. Well,
it's like
you guys,
everything that could break. I plugged my camera in, it didn't come on. I'm like, why?
Well, you guys have a great rest of your night tonight. See ya. See you next time.
Have a nice evening, Matthew. Get some good rest.
Thank you.
So Tim, I'm just curious. Do you remember back in the late '80s, early '90s, there was a guy who was trying to develop a flying car? I think it was in like Davis, California.
Paul Moeller.
Yeah, the Moeller. Yeah,
the Moeller Sky Car.
Yeah.
See, you didn't even have to say. You just remember there was this guy. Yeah, he was on like every magazine. He was using the Rotax engine. Did I interview him? I may have interviewed him back in the day. I talked to him a few times.
Okay.
He had the Rotax engine. He was the crowd favorite too. He had funding. He was kind of like almost a little bit like Burt Rutan. He started doing this in the 60s and he worked on it for a long time. He pioneered all these fiberglass techniques and all that kind of stuff.
Yeah.
Yeah, the challenge with the gasoline ones was power to weight ratio, if I remember right.
Right, the Moeller Sky Car, I remember that.
Yeah, and it did have 4 engines, just like today's drones.
Yeah.
And I saw video, I think he passed away. I saw a video of the person who took his company over, and they actually had one of these levitating and moving around, but they said that it was tied down for insurance reasons. And again, I would bet you, I mean, this thing was built like a Corvette. So the insurance was probably based on like what happens if it crashes, how much are you out for that much fiberglass?
Yeah.
Yeah, I'm a big fan of EVTOL stuff though. I mean, you know,
yeah,
because
I spent a lot of time and effort on the Moeller Sky Car over the years because my first love was aviation. I actually have propulsion degrees. So they needed 100. They needed the same thing that BD5. The BD5, they turned it into a jet, but before it was a jet, it was a little BD5 aircraft. They needed a 100-pound, 100-horsepower engine that, was not in existence. Curiously enough, I just saw an advertisement, or just saw a thing. Again, the internet is amazing for keeping you up to date on ridiculously useless things. That some guy just built a 100 or 38 horsepower, 38 pound. I don't even want to call it a 4-stroke, but it's a multi-stroke engine. But the energy is this way. It's not rotary. It goes back and forth, back and forth, back and forth.
Yeah.
And it's got a rotating set of loads and then a bizarre ass cam in the middle and something curious. But scaled up, that would be a 100-pound, 100-horsepower engine, which is what you need for the Moeller thing. With today's, with today's electric technology, you just need a really good generator to provide the energy to run the electric motors. 400-volt systems. You could build a nice quadcopter today, which is what they're doing. They're going with lithium-ion batteries, and they're skipping the whole gasoline sector. But there's a lot to be said for having a combustion engine there, providing all your energy that you need for your electric drive. There's a lot to be said for that. But there's nobody putting any money into that. It's all going into the all electric aircraft, which they might be. I don't know. they need to do about a 3x on the energy density to get serious about it. My 2 cents.
Well, I think, guys, I'm going to have to do a really big update on Alzathon and on the invisible wall experiment. I've been kind of out of APEC for the last 2 months because of summer and kids and family and everything. But maybe, Tim, maybe it's time to do like a full 1 hour session, and I'll show you guys what's been going on. There's a lot of things going on. We've got our Jewish space laser almost totally up and running. That's for
Mark. Do you want me to put you in for August 30th?
August 30th is not good. No, it's got to be
September 27th.
Yeah, maybe September 27th. I think you guys are going to be here then too.
Okay.
That's when we're going to have like a meetup. But yeah, maybe September 27th would be a good time. August 30th is back to school, and I'm probably going to be doing stuff with the kids that weekend too.
Yeah, I mean, there's a lot of stuff going on right now. One of the reasons I'm so wiped out is like just trying to stay on top of stuff this weekend. You know, again though, that Casimir stuff that kind of came out of left field. I'm super excited about that.
Yeah, I mean, I've seen a propellantless propulsion device using Casimir thrust that was built at my lab by another guy.
The Fresnel lens. Right?
Yeah, the Fresnel lens idea, the asymmetric Fresnel lens Casimir cavity. So it doesn't surprise me. The scalability of it is a question, because I don't know whether has he stacked them yet, or I know he said he stacked them, but like Drew ran into problems with stacking, and based on what we know of like macro scale Casimir effect, like with ships in a harbor, because the harbor effect and the Casimir effect are pretty much the same thing, just one's on nanoscale and one's on macro scale. That doesn't stack.
Well, I think he's doing 2D arrays on chips. I don't think he's done 3D yet, but I could be mistaken.
Yeah, if it's not stackable, then he runs a problem of running out of surface area before you can do anything with it.
Yeah, I pretty much beat stack problem, Mark.
You beat your stack problem.
I do.
Yeah, I
I
beat my
just
stack
think
problem. Yeah, I don't know about
here's
yours.
what gets me. I used to watch Stargate towards the latter seasons when they really ran out of plot ideas, right? They brought in the ZPE generator in the later days of Stargate. They're like, yeah, hook up the ZPE generator. And I was like, okay, that ruins the plot. We know that isn't real. They're like, yes, of course it does this. Dude, now it's real. Except that, like, instead of powering the Stargate, it basically powers a calculator watch. But,
No, not even. Not even. It's nowhere near that power level. It's
a really small Stargate.
No, it's like it's on the order of the stuff Michael Perrone was dealing with.
No, it's so what he was saying was, it was either him or Garrett Modell were saying that you could consider it comparable to solar cells, and again, it's each of those diodes, each of those junctions, right, is a tiny fraction of power. But then when you start to do these 2D rays, you can get it up closer to a solar cell. So yeah, you're not going to fly through the universe with it, but I think the idea is exciting.
Yeah, it definitely is very exciting. If you want to talk to somebody about 0-point energy, you should talk to Stephen Greer. That's been his bread and butter, yapping about that for years. He loves talking about 0-point energy.
Yeah, I will refrain from bugging Greer.
The day Tim Ventura gets Stephen Greer on his podcast. That will be an interesting one. You got to appeal to the ego.
I would love to hear an actual experimental setup from Greer about it, because he's talked about it a lot, but on the actual like engineering side, like, yeah, you need something this size doing this. I've never heard anything like that.
You're not gonna get any of that stuff. What you'll get is he'll talk about the big names that we've all heard of already, and
Yeah.
just repeat their claims. I don't think he has anything, but he might. He might.
No, I don't think
He
technical.
is. He's kind of like Jeremy Reese with, times 100 on the ego. He's a lightning rod for this type of people, the people that are interested in 0-point energy stuff. So there's a lot of people whispering in his ear, and I'd be curious what names he would drop, if there's anyone new or if there's any technology that he knows of that,
Wait, here,
And
I'll put the.
Bob
I
Lazar
don't
has
think
something
that's
to
the
say.
real Bob Lazar. I think that's imposter Bob Lazar or fake Bob Lazar.
Oh, wait, if it's the real Bob Lazar, how much of a discount did you give me on the Mercury? Okay, if he can answer that, it's the real Bob Lazar. Let's see.
I gotta tell you, I've lived on a private airfield for about 25 years, and the rate at which I use my aircraft on my private airfield, which is about as easy as it gets to use your private aircraft, is almost zero. It's
The
really
last
sad.
time I saw your airfield, though, it had not been mowed.
And you came during a very brief period between mowings, because it gets mowed about every other week. But the little bit of grass ain't going to stop an airplane from moving. It's the will to use your toys and the time to have to do it. So even if I had a spaceship that could take me to Mars in 3.5 days, I don't get 3.5 days to go to Mars very often. So,
And
I
for the
gotta retire.
But
For the
still,
fly-
isn't that like, just think about it. You're like, I'm too busy to go to Mars right now.
I am.
I'll go
too
next
busy
week.
to go to Mars. I
I'll
want to
do
go to
next
Titan.
week.
I don't have 2 weeks to do that. A 2-week trip out to Titan.
Drew, is your airplane operational?
Just depends on your viewpoint. I'd say no right now.
has it had an annual?
No, it's not. Not in a while.
Yeah.
It used to be absolutely pristine, but life happens and things change.
But as far as the flying car conversation that y'all were having when Szydagis was here, a lot of folks don't appreciate like how hard and dangerous flying is, right? And that's with like 0.1% of the population is a pilot, right? So now if you had as many pilots as drivers, right, you're gonna have a lot more deaths. No matter how safe they make it, you'd have a lot.
You
more
would
deaths.
have to
It
start
has to be
with
automated. It has
right.
to be
You'd have to
automated.
start with the whatever they are, the Tesla bot cars or whatever the hell. You don't get to drive the machine drives. That's where you have to start.
Automated doesn't make the ground come at you any slower.
No,
Oh, believe me, there's too many stupid people to be putting them all up above.
They went through this
ground.
back in the they went through this back in the 2000s. Back in the Paul Moeller days, they went through this. It was so the issue they had, it was the same thing. It was getting a pilot's license takes hundreds of hours of flight time, and it's too much for most people. And 40. So
40, about 48.
And
get a pilot's license.
plus study, plus the course,
plus a lot of study.
Yeah,
and you really got to want to do it because it's expensive and it's useless when you get it, and you really better love aviation going in because you're going to hate it by the time you get done.
And then around that time they put in the light aircraft control system, I think. And
hold up,
if I remember right, they made a decision.
Mark.
Yeah.
Bob said 17% for your Mercury. He said as real as 115, boys, 17%.
Mark doesn't remember.
I don't remember.
You don't remember?
Not off the top of my head. I'll have to check my email. I'll have to check my email for that one. But we could. I will know in a few minutes.
Who is this Bob Lazar guy?
Bob Lazar is like the world's first UFO engineer. Well, I first read about him in I don't remember, 89, I think, Omni magazine.
90.
I'm gonna go check. Okay, I'll be right back.
Okay.
I think it was Omni magazine.
Where's his UFO?
Area 51. That
It-
Bob started the Area 51 mythos. That all came out of the Bob Lazar story.
He spent he went over there like 9 times, 8 or 9 times, the way he tells it. Went over there 8 or 9 times in like the middle of the night. He'd go there for, however many hours to work on the propulsion mechanism that they had. He's the Element 115 guy that said there were these little triangle cutouts of sliced out of this block of stuff that is up way high in the island of stability, and that when you set it down inside this little reactor ball thing, it starts creating anti-gravity. Like he threw a ping pong ball or golf ball at it, and it just like got deflected and shot into the ceiling. Like he tried to put his hand close, and the hand gets like repelled. Like that was all what he was saying, was that this stuff, like you can't get it on Earth, you can't make it on Earth. The aliens, you only get this when you shoot down an alien, flying saucer.
Yeah.
So
That's Area 51. And then Jared's man crush, Friedwart Winterberg, was at like Area 52 and a half. And we did all that research. And yeah, and his claim to fame. So instead of going to Area 51 where the good stuff is, we got to study the guy who was studying slime molds at Area 52 and a half because he did environmental contamination.
Environmental contamination. No, it was over in the like Yucca Mountains or something, was where they were supposedly putting like the barrels of used uranium or whatever, used nuclear fuel. But Friedwart Winterberg, among his many accolades, one of the other things he came up with was how to, so underground nukes, they figured out that you can direct a nuke, 3rd generation style, right? And you can like bore a tunnel, right? And it melts all of the stuff that bores the hole. Well, he figured out how to double the amount of energy by reflecting all the energy when it explodes to create a reflector. And so he like doubled the efficiency of creating these underground tunnels for the deep underground military bases. And then he ended up going in the late 80s. He was among his many trips to Area 51. He started writing papers around that same time that he was doing like cleanup or figuring out the groundwater thing. And he was really into rocks, but I don't know.
That's not Bob Lazar. Bob Lazar gave me a better discount than 17%.
We will call it current status unknown Bob Lazar. I'm not going to call him fake Bob Lazar. I'll call him current status unknown. That's definitely
not Bob Lazar. And also, he didn't calculate it by percentage. We just went for a round number. So I don't think even Bob knows what percentage it was. He knows what number it was. So I gave way too many clues. We already know that's not the real Bob Lazar.
I think that I heard this name before. Is Dr. Charles. That thinks he's figured out what the drawings mean. We had this long, detailed conversation, and he's all into ufology and I don't know, aliens on top of pyramids and stuff. But it was something about the center of the Lazar tube or something being a waveguide, and
the real Bob Lazar would be hanging out with Jeremy, Kenyon, Lockyer, Steven Seagal, Corbell, not with us.
Will the real Bob Lazar please stand up?
Stand up.
Mark, you need to feed that dog. He's looking thin.
She is a very healthy weight, and she always has food in her bowl. But she did eat a lot of pork when Tim came. Tim was trying to get her fat, and it was not successful.
Where'd all the bacon go, guys?
This has been great. I have to go. I don't know what I got to do, but I got to go do something. I've been in this chair too long.
Well, Drew, thank you, man. Thank you.
Y'all have a great evening. Good luck, and I'll catch you on the next run.
Yeah. Well, and thank you to all of you guys. Thank you for all. And
hey, Jared,
thank you for your patience.
We need to plan a future. Madness.
Yeah. You need to come to New Jersey at some point. I came to Florida.
Yeah, Mark, give me a call later too. We need to loop you into this madness.
Oh, we did. This is the latest addition to the camping van. We started putting stickers on the truck.
Nice. All right. Well, shall we wind it down, guys?
Yeah. Well, thank you to everybody. Thank you to the audience. Thank you for the guys in chat for your patience, if nothing else. So, yeah, I mean, you guys already know that I'm an idiot, so that goes without saying. But I'll just repeat that for the record that I'm an idiot. And
Tim, you are awesome. You make this happen.
You just said that because nobody else disagreed. They're like, "Yep, Tim, you are an idiot."
Okay, I'm gonna head out, guys. Live long and prosper.
Okay, well, let me close things down. I'm going to end the stream. This has been APEC for August 2nd, 2025. We did have some amazing stuff today, a little bit disorganized. And then let me see again on August 30th, I think, right, Curtis? Then you can do the full unified theory presentation. And I'm glad that the other stuff is taken care of and turned out not to be a big issue. But so thank you guys. And that's it for today.